Welcome to the Sleepless Universe. In this video, we'll explore the fascinating idea that the universe might never have had a beginning, diving into theories of eternal time, cyclic cosmos, and infinite cosmic history. If you enjoy this kind of content, I'd really appreciate a like and a subscription. Also, let me know in the comments where you're watching from. Now, I wish you a lot of relaxation and enjoyment as you listen. The question of eternal time. From the earliest days of human thought, the question of where everything came from has haunted our minds. Whether we looked up at a starlit sky in the deserts of Mesopotamia, contemplated the ocean horizon from an island in Polynesia, or sat beside the flickering fires of ancient Europe, the mystery was the same. Did all of this have a beginning, or has it been here forever? The modern sciences, cosmology, astrophysics, particle physics, have tried to bring clarity to this timeless puzzle. Yet even with satellites mapping the edges of the observable cosmos and particle accelerators probing the smallest known structures, the question of the universe's origin remains one of the most profound and unsettling in human knowledge. In popular culture and in many classrooms, we are taught that the universe began with the Big Bang. According to the standard cosmological model, some 13.8 billion years ago, space, time, matter, and energy all erupted from an unimaginably hot and dense state, expanding and cooling into the vast cosmic web we inhabit today. This story has tremendous observational support. The cosmic microwave background radiation, the abundance of light elements like hydrogen and helium, and the large-scale structure of galaxies all match the predictions of Big Bang cosmology. Yet the Big Bang theory, as successful as it is, does not truly describe the beginning. Instead, it describes the universe from a fraction of a second after whatever that beginning was. What happened before that fraction of a second, or whether the concept of before even makes sense, is still wide open to speculation and debate. Some scientists, philosophers, and theologians have argued that the very idea of a beginning might be an illusion born from our human experience of time. After all, we live our lives within a framework of cause and effect. Each event we witness has something that came before it. The sun rises because the earth rotates. The earth rotates because of the conservation of angular momentum from its formation, and so on. Tracing this chain backward, it feels natural to imagine a starting point. But perhaps time itself is more like a circle than a line, or perhaps it stretches endlessly in both directions. If that is the case, the universe might never have had a first moment. This notion is not without precedent. In various cultures across history, myths and philosophies have entertained the idea of a cosmos without origin. In Hindu cosmology, for instance, there is the concept of kalpas, immensely long cycles of creation and dissolution, suggesting that the universe has neither an absolute beginning nor an ultimate end. Ancient Greek thinkers like Aristotle also believed in an eternal universe, uncreated and everlasting. These ideas often emerge independently in different civilizations, hinting at the deep intuitive pull of imagining reality as something without birth or death. Modern cosmology, armed with mathematics, telescopes, and computer simulations, has revisited this old intuition with new tools. The question has evolved from, did the universe have a beginning, to, is a beginning even necessary for our theories to work? This is where alternative models come in, ideas that propose the cosmos might have existed forever in some form, even if it looked very different from what we see today. Such models are not just idle speculation. They often emerge from attempts to solve specific puzzles in physics. For example, the problem of singularities, points where our equations break down, has pushed theorists to consider scenarios where the Big Bang was not the ultimate starting point, but merely one stage in an ongoing process. The human fascination with infinity plays a role here as well. Infinity is both alluring and troubling. Alluring because it removes the awkward question of what came before the beginning, and troubling because it challenges our ability to make sense of the past. In a universe without a start, there is no first cause, no initial spark to trace everything back to. This can be unsettling for those who seek a neat, definitive answer, but it also opens the door to a richer and more mysterious picture of reality. Before diving into the specific scientific models that attempt to describe a universe with no beginning, it's worth exploring why this question is so hard to answer in the first place. Our observations are limited by the speed of light and the age of the universe as we can measure it. The cosmic microwave background marks the furthest we can see with light, a wall beyond which photons have not yet reached us since the early universe became transparent. Beyond that lies the realm of pure theory, where equations must do the heavy lifting without direct observational support. And even within the observable range, every measurement we make is subject to the distortions of cosmic expansion, gravitational lensing, and other effects that complicate the picture. Complicating matters further is the possibility that our intuitive understanding of time may not apply to the cosmos as a whole. In relativity, time is not absolute. It flows differently for observers in different states of motion or gravitational environments. In quantum mechanics, time can even lose its usual meaning entirely, especially near the Planck scale, where space-time may no longer be a smooth continuum. If time itself is emergent, arising from more fundamental relationships, then asking about a first moment might be like asking about the edge of the Earth. The question presumes a structure that simply isn't there. Some physicists propose that the origin question might be unanswerable, not because of technological limitations, but because of the nature of the laws of physics themselves. Theories that unify quantum mechanics with general relativity, such as loop quantum gravity or certain string theory approaches, sometimes predict that the universe has no singular origin point at all. Instead, there may have been a prior phase, or an endless sequence of phases, stretching back indefinitely. If such models are correct, the cosmos could be infinite in both space and time, though possibly in ways that defy straightforward visualization. The challenge for any no-beginning model is to remain consistent with the enormous body of observational data we already have. It's not enough to say, the universe has always existed. One must explain why it looks the way it does now, why galaxies are distributed in a certain pattern, why the cosmic microwave background has the specific temperature and fluctuations we observe, and why the laws of physics seem to be the same everywhere we look. This is where the creativity of theoretical physics shines, as scientists attempt to build models that fit the facts while breaking free from the constraints of a cosmic starting gun. As we move forward in this chapter, we will explore the major contenders in this fascinating field: the cyclic universe, the steady-state theory, and quantum cosmological models that eliminate the need for a first moment. Each offers its own vision of eternity, grounded in mathematics but inspired by the same ancient wonder that drove early humans to look up at the night sky and ask, how long has this been here? And perhaps more importantly, how long will it remain? When considering a universe without a beginning, one of the first concepts to confront is our human bias toward thinking in terms of sequences. In daily life, we measure time with clocks and calendars, always moving from one moment to the next. We recall yesterday, live today, and anticipate tomorrow. This structure, so ingrained in our minds, pushes us to imagine the universe as following a similar arc, one that must start at some defined point before continuing into the future. But on the cosmic scale, this familiar sequence may not apply at all. Time could be more like an unbroken fabric, with no clear start or end, stretching indefinitely in both directions. To imagine such a reality, it helps to think of analogies that loosen the grip of linear time. Picture a circle. There is no first point on its circumference, only an endless loop in which any point can be arbitrarily designated as the beginning. Similarly, the universe might be a self-contained system where earlier and later are relative, but there is no absolute origin point. This idea can be extended even further. Perhaps the cosmos is not just cyclic in space and time, but in its very physical states, endlessly shifting between phases of expansion, contraction, transformation, and rebirth. Scientific interest in cyclical or eternal models is partly driven by the difficulties inherent in describing an absolute beginning. The classic Big Bang model, when extrapolated backward, arrives at a singularity, a point of infinite density and temperature, where our current physical theories break down. At that singularity, the equations of general relativity lose predictive power. Many physicists view this as a sign that the model is incomplete. that something else must happen before the moment we call time zero. Removing the singularity often requires imagining a preceding era, which naturally opens the door to scenarios without a true starting point. One such scenario is the oscillating or cyclic universe model. In its simplest form, the universe alternates between periods of expansion and contraction. After expanding for billions of years, gravity eventually slows the expansion, halts it, and reverses it, causing the cosmos to collapse back into a dense state, a big crunch. But rather than ending there, this dense state somehow rebounds, triggering another expansion, another cycle, another cosmic epoch. In some versions of the model, this has been happening forever, with no first cycle and no final one. The universe is like a heartbeat that never began and never stops, only pulsing through its infinite rhythm. While elegant in concept, cyclic models must wrestle with a number of physical challenges. One is entropy, the measure of disorder in a system. In each cycle, entropy tends to increase, leading to the so-called heat death problem. If the universe has been cycling forever, how has it avoided building up so much entropy that future cycles become impossible? Various modifications attempt to solve this by introducing mechanisms that reset or dilute entropy between cycles, or by suggesting that each new cycle expands more than the last, effectively dispersing disorder into unreachable regions of space. Interestingly, cyclic ideas have counterparts in ancient thought. Hindu cosmology describes cycles of creation and destruction, each lasting billions of years, overseen by deities but operating according to eternal laws. The Maya also envisioned time as a series of repeating ages. These cultural parallels do not constitute scientific evidence, but they do show that the concept of endless recurrence is deeply embedded in human imagination, resurfacing again and again across continents and centuries. Beyond cycles, another influential framework for an eternal universe is the steady-state theory, which emerged in the mid-20th century as an alternative to the Big Bang. In the steady-state model, the universe is expanding, but its large-scale appearance remains constant over time. This is achieved by the continuous creation of matter to fill in the gaps left by expansion, keeping the average density of the cosmos the same. If true, this would mean the universe has no beginning or end. It looks roughly the same at all moments in its history, and it has always been that way. The steady-state theory was appealing because it avoided the philosophical implications of a beginning, fitting neatly into a vision of a timeless cosmos. However, as astronomical observations improved, evidence mounted against it. The discovery of the cosmic microwave background in 1965, a relic glow from a hot, dense early phase of the universe, was particularly damaging to the steady-state model, which predicted no such radiation. The observed evolution of galaxies over cosmic time also contradicted the steady-state prediction of a uniform appearance. While the theory is now largely discredited, it remains historically significant as a serious scientific attempt to envision an eternal cosmos. Even though the steady-state model itself has fallen out of favor, some of its conceptual descendants persist in modern cosmology. Certain inflationary models, for instance, suggest that the universe, or multiverse, could be eternally inflating, with local regions periodically budding off into distinct universes. In such frameworks, the inflationary process has no beginning, and while individual pocket universes like ours have finite ages, the overall multiverse has existed forever. These ideas bring us into the territory where cosmology blurs into philosophy. If time stretches back infinitely, what does that mean for causality, for meaning, for the very structure of reality? In an eternal cosmos, every event, no matter how improbable, could occur not just once, but infinitely many times. There could be infinite versions of Earth, of you, of this very moment, scattered across the boundless reaches of time and space. Such implications are mind-bending, and they raise questions about the uniqueness of our experience and the significance we attach to it. The challenge is that infinity can be treacherous territory for both mathematics and human intuition. Infinities appear in equations, sometimes signaling profound truths and sometimes revealing that the model has been pushed beyond its limits. Philosophically, infinity can be comforting. It ensures that nothing ever truly disappears. But it can also be unsettling, suggesting that our lives might be but one flicker in an unending procession with no ultimate purpose. The tension between these emotional responses mirrors the scientific tension between the elegance of eternal models and the stubborn constraints of observational data. As we move deeper into this chapter, we will encounter the quantum models that have taken up the torch of no-beginning cosmology, building on the limitations of classical theories to create scenarios where time may be an emergent property, not a fundamental one. These models suggest that asking, "What happened before the Big Bang?" might be like asking, "What's north of the North Pole?" A question that seems meaningful only until we understand the shape of the system we're describing. Quantum cosmology takes the discussion of a universe without a beginning into even stranger territory. At the smallest scales imaginable, the Planck length, space-time itself may no longer behave like the smooth fabric described by Einstein's general relativity. Instead, it could be foamy, jittery, and fundamentally uncertain, shaped by the probabilistic rules of quantum mechanics. In this regime, our familiar concepts of before and after may simply not exist in the way we understand them. Time might not be a continuous arrow, but an emergent feature that arises only when we zoom out to larger scales. One of the most famous proposals in this domain comes from physicists James Hartley and Stephen Hawking, the no-boundary or Hartley-Hawking state. In this model, the universe is finite but has no boundary in time, much like how the surface of a sphere is finite in area but has no edge. Just as you can walk around the Earth indefinitely without falling off, you could, in principle, trace the history of the universe without encountering a first moment. Time, near what we think of as the beginning, blends smoothly into a kind of spatial dimension. In this picture, asking what happened before the Big Bang is meaningless because there was no before in the conventional sense. Another intriguing approach comes from loop quantum cosmology, an application of loop quantum gravity to the entire universe. This framework suggests that the Big Bang singularity is replaced by a big bounce. According to this model, the universe may have been contracting before our current expansion, reaching a minimum size before bouncing outward again. The bounce is not a singular beginning, but a transitional moment between a previous cosmic phase and the one we observe today. If the process of contraction and expansion has been occurring forever, then the universe truly has no first moment. It is eternal in both directions of time. In addition to these models, there are also proposals rooted in string theory and higher dimensional physics. Some versions of string cosmology envision a pre-Big Bang phase where the universe existed in a different state, perhaps as a collection of vibrating strings, or as a higher dimensional brane in a larger dimensional space. Collisions between such branes could trigger Big Bang-like events without requiring a singular origin. If such collisions happen eternally in the larger framework, our universe's apparent beginning might just be one of countless such events. These quantum models are not only attempts to remove the singularity problem, but also to reconcile general relativity with quantum mechanics, the two great pillars of modern physics. The tension between these theories becomes especially acute at extreme energies and densities, such as those at the Big Bang. By replacing the singularity with a bounce, a smooth transition, or a timeless state, these models hope to create a more complete and self-consistent description of the cosmos. However, quantum cosmology also faces unique challenges. Testing these models is extraordinarily difficult because they often make predictions about conditions that existed before the earliest light in the universe. The cosmic microwave background was omitted. Without direct observational access to this era, scientists must look for subtle imprints or indirect evidence that could distinguish one model from another. This might include patterns in the distribution of galaxies, tiny variations in the cosmic microwave background, or even signals in the gravitational wave background that could carry information from the universe's earliest moments. Some theorists argue that the universe could be past infinite in a statistical sense, even if it has a finite age in our specific cosmic region. In an eternal inflation scenario, for example, the multiverse could be expanding forever into the future, and might also have been doing so forever in the past. Our observable universe would then be a bubble nucleated within this eternal process, a bubble that has a beginning, but within a broader reality that does not. This is a subtle distinction. While our patch of the cosmos might be only 13.8 billion years old, the larger framework could have no age limit at all. Eternal inflation also brings us into contact with philosophical puzzles such as the measure problem. If there are infinitely many universes, how do we meaningfully talk about probabilities? In an infinite set, every possible event happens infinitely often, making it difficult to define what is typical or rare. This ties back to the broader challenge of reasoning about infinity, an unavoidable theme when discussing a cosmos with no beginning. Critics of the no beginning approach sometimes point to the Borde-Guth-Vilenkin theorem, which states that any universe that has, on average, been expanding throughout its history must be geodesically incomplete in the past. That is, it must have a boundary in time. While this seems to imply a beginning, proponents of eternal models counter that the theorem's assumptions may not apply to all scenarios, especially those involving contracting phases, non-standard definitions of time, or emergent space-time frameworks. The debate over how to interpret and apply the BGV theorem remains lively. In many ways, the exploration of a universe without a beginning is as much a philosophical endeavor as a scientific one. It forces us to confront the limits of our knowledge and to examine the assumptions embedded in our theories. The very notion of a start might be a conceptual artifact, rather than a feature of reality. This is why so many different branches of physics, classical cosmology, quantum gravity, string theory, and even thermodynamics, intersect in this discussion, each offering a different lens through which to view the problem. As our observational tools improve, through more precise cosmic microwave background measurements, gravitational wave observatories, and deep galaxy surveys, we may find new ways to test these bold ideas. It is conceivable that within a few decades, we will have enough indirect evidence to favor one class of models over another, or even to rule out certain eternal scenarios entirely. Until then, the question remains open, inviting both scientific rigor and imaginative speculation. This middle ground, where hard physics meets profound philosophical questions, is where cosmology is at its most captivating. A universe without a beginning challenges not just our theories, but our place within them. It invites us to see ourselves not as actors in a finite story with a first page, but as participants in an endless epic that has been unfolding forever, in ways we are only beginning to glimpse. If the universe truly has no beginning, then every event we witness or imagine would be just one frame in an eternal reel. In such a cosmos, the question, why is there something rather than nothing, becomes even more intriguing. If existence has always been, then nothing may never have been a real possibility. In fact, the very concept of nothing might be ill-defined, a philosophical abstraction that has no counterpart in the physical world. For some, this realization is liberating. It eliminates the need to account for a first cause. For others, it is deeply unsettling as it denies the comforting notion of an origin story. An eternal universe also changes how we think about uniqueness. If time stretches back infinitely, the sheer vastness of possibilities suggests that patterns, whether physical structures, planetary systems, or even conscious beings, could repeat. Somewhere in the infinite past, there may have been arrangements of matter identical to those we see now. Somewhere else, there may have been arrangements almost identical, but with slight differences. Another Earth where events unfolded just a little differently. In this view, the history we know is just one of countless variations, each embedded in an infinite expanse of time. These possibilities lead naturally to the idea of recurrence, a concept famously explored by Friedrich Nietzsche in his thought experiment of the eternal return. While Nietzsche's purpose was philosophical, the concept resonates with certain physical models. In a perfectly deterministic finite system with infinite time, states will eventually repeat, not because of mystical cycles, but due to the mathematics of probability. However, whether the universe meets the conditions for such repetition is still unknown. If the cosmos is infinite in both time and space, with continually changing conditions, exact recurrence might be impossible. Still, the mere chance that history could repeat lends a strange symmetry to the idea of eternity. The psychological implications of an eternal universe are profound. For civilizations like ours, which measure progress against the backdrop of a finite history, The notion that there was no true start can be disorienting. Our narratives, whether religious, scientific, or cultural, often anchor meaning in origins. The creation of the world, the birth of life, the dawn of humanity. Without a clear origin, meaning must be sought in patterns, processes, and relationships rather than in a single defining moment. Some may find this shift freeing, as it removes the pressure of a definitive cosmic purpose. Others may find it unsettling, as it undermines the story-like arc we often project onto reality. On the scientific side, a universe without a beginning presents a different kind of challenge, explaining its stability over infinite time. If the cosmos has existed forever, what prevents it from drifting into a state of complete disorder or collapsing into a lifeless uniformity? Many eternal models address this through mechanisms that maintain dynamic structure, expansion, energy exchanges, or phase transitions that continually refresh complexity. These mechanisms are not just theoretical patches, they are attempts to reconcile the observed richness of the cosmos with the mathematical demands of an infinite past. Even with these models, the problem of observational access remains. We can only see a limited portion of the universe's history, bounded by the speed of light and the age of the observable cosmos. This means that evidence for or against an eternal past will likely remain indirect. Subtle features in cosmic background radiation, distributions of matter on the largest scales, and patterns in gravitational waves may provide clues, but they will never give us a direct view of infinity. The challenge is to interpret these faint signals without overreaching, grounding speculation in what the data can actually support. Philosophically, the absence of a beginning forces us to reconsider causality itself. In everyday life, causality is a chain. Each event is linked to something that came before it. But in an infinite regress of causes, there is no first link. This raises the possibility that causality might be a local, emergent feature rather than a universal law. In other words, what we think of as cause and effect may only apply within certain regions or epochs of the cosmos, not to the whole of reality. This would be a radical shift in our understanding, one that could ripple into every branch of science. If there is no ultimate origin, then the laws of physics themselves may be part of an eternal framework, uncreated and unchanging. Or they may evolve over infinite time, with different eras governed by different rules. The latter idea opens another layer of speculation. Perhaps the laws we observe are temporary, shaped by the conditions of our particular cosmic epoch. In an earlier, or later, phase of the infinite universe, entirely different laws might reign, giving rise to structures and phenomena beyond our comprehension. For now, these ideas remain speculative, constrained by both our technological limits and the difficulty of reasoning about infinity. Yet the pursuit of answers continues, driven by curiosity as old as humanity itself. Whether the cosmos had a beginning or has existed forever, the journey to understand its nature is itself a defining feature of our species. We are creatures who look back, who ask where we came from, who try to see past the horizon of the knowable. Even if that horizon stretches forever, the act of seeking gives meaning to the quest. In the end, contemplating a universe without a beginning may tell us as much about ourselves as it does about the cosmos. It reveals our deep desire for stories, our struggle to grasp infinity, and our willingness to imagine realities far beyond our direct experience. It challenges us to accept that some questions may never have definitive answers, and to find beauty in the mystery itself. For perhaps the most remarkable thing about an eternal universe is not that it has no starting point, but that in all its endlessness, it still contains moments like this. A conscious mind wondering about its place in a reality without end. The Cyclic Universe. For most people who first hear about it, the Cyclic Universe sounds like something lifted from myth rather than science. A vision of the cosmos endlessly repeating itself in grand sweeps of creation, destruction, and renewal. Yet this concept, though ancient in origin, has found new life in modern cosmology, not as a poetic metaphor, but as a serious scientific contender for explaining the deep past of the universe. At its heart, the cyclic model proposes that what we perceive as the beginning of our universe may simply be the latest in an infinite series of expansions and contractions. In other words, The Big Bang might not have been the birth of everything, but merely a transitional phase between what came before and what comes after. The appeal of a cyclic cosmos is multifold. It sidesteps the uncomfortable question of what came before the Big Bang by suggesting that there was no before in the absolute sense, only the preceding cycle. It provides a framework in which the universe's history extends infinitely into the past, removing the need for a singular origin event. And it can, in principle, account for the observed large-scale uniformity of the cosmos, as each cycle could smooth out irregularities before the next begins. The most straightforward version of the cyclic model is the oscillating universe scenario. In this picture, gravity is the master architect, ultimately halting the current expansion of space and reversing it into contraction. As the cosmos shrinks, matter and radiation grow ever denser and hotter until, at the point of maximum compression, a big crunch occurs. But instead of ending there, the energy of this collapse triggers a rebound, a big bounce, that launches the universe into a fresh expansion. Each bounce erases the previous cycle's structures, setting the stage for galaxies, stars, and planets to form anew. Early 20th century versions of the oscillating universe arose naturally from Einstein's general relativity. Solutions to his equations showed that, depending on the amount of matter and the strength of cosmic expansion, the universe could oscillate forever. For a while, this idea was attractive to those seeking an eternal cosmos. But as astronomical measurements accumulated, the balance tipped against it. Observations indicated that the universe's expansion is not slowing down under gravity's pull, but accelerating due to a mysterious component called dark energy. In a simple oscillating model, acceleration is a deal breaker. If expansion is speeding up, it may never reverse into contraction. However, acceleration does not necessarily kill the cyclic idea. It just forces a more sophisticated approach. Modern cyclic models incorporate dark energy into their framework, sometimes in the form of a scalar field whose properties change over time. One such model is the ekpyrotic scenario, inspired by string theory. In this model, our universe is a three-dimensional brane floating in a higher dimensional space. Cycles occur when our brane collides periodically with another parallel brane, generating conditions similar to a Big Bang. These collisions happen not once, but endlessly, producing a series of expansions like chapters in an infinite book. The ekpyrotic model offers a bonus feature. It can potentially solve the flatness and horizon problems, issues also addressed by inflationary theory, without requiring an inflationary phase. The slow contraction phase before each bounce, as described in the ekpyrotic setup, smooths and flattens the universe, preparing it for the next expansion in a way that matches observations. This slow contraction is crucial because it can dilute unwanted irregularities and suppress the growth of inhomogeneities that would otherwise make the cosmos wildly uneven. Entropy poses another challenge to cyclic cosmology. In thermodynamics, entropy, often described as disorder, tends to increase over time. If the universe has been cycling forever, wouldn't entropy build up to the point where future cycles become impossible? Classical thermodynamics suggests that over an infinite number of cycles, the universe should reach a state of maximum entropy, heat death, where no useful energy remains to power stars or other complex structures. Cyclic models must find a mechanism to reset or dispose of excess entropy. Several strategies exist to tackle the entropy problem. One is that each cycle is larger than the previous one, with the expansion phase dispersing entropy into regions beyond our observational reach. Another is that certain processes during contraction, perhaps involving exotic physics, could reduce the total entropy. Some proposals even suggest that what we call entropy might not behave the same way on cosmological scales as it does in closed laboratory systems, leaving room for unconventional solutions. Historically, the cyclic idea predates modern physics by millennia. Ancient Indian cosmology described vast cycles of creation and destruction, kalpas, spanning billions of years. The Stoics of ancient Greece envisioned the universe periodically consumed by a cosmic fire, ekpyrosis, before being reborn. These ancient visions are not scientific in the modern sense, but they share with contemporary models a fascination with recurrence and renewal, suggesting that the intuition for cycles runs deep in human thought. One of the most compelling aspects of cyclic cosmology is its narrative symmetry. In our current standard cosmology, the universe is a one-way street. It starts with a bang and ends with a whimper, either in a heat death, a big freeze, or a big rip. In a cyclic universe, the road loops back on itself. Death is not an end, but a prelude to rebirth. And the cosmos is not a linear story, but an infinite poem with repeating stanzas. While this is aesthetically appealing, aesthetic appeal is not enough. Such models must still make testable predictions and survive confrontation with data. Some predictions of cyclic models overlap with those of inflationary theory, making them difficult to distinguish observationally. Both can produce a flat, homogeneous universe with small fluctuations that seed galaxy formation. However, the fine details of these fluctuations, their statistical properties, their distribution on the largest scales, could differ subtly between models. Detecting such differences requires high-precision measurements of the cosmic microwave background and large-scale structure, something future space missions and ground-based observatories are aiming to achieve. The prospect of confirming or ruling out a cyclic model is tantalizing because it would reshape our understanding of cosmic time. If a bounce can be established with reasonable certainty, it would imply that our universe's history stretches infinitely into the past, fundamentally altering the context in which we place our own existence. The story of the cosmos would become not a singular tale of origin, but a chapter in an endless saga. The deeper one examines the cyclic universe, the more it becomes clear that this idea is not a single model, but a family of related concepts, each attempting to solve the same core problem in different ways. All of them share the fundamental premise that the universe undergoes repeated phases of expansion and contraction, but they differ in the physical mechanisms driving those transitions and in the nature of each cycle's reset. Some are rooted in classical general relativity, others in speculative high-energy physics, and still others in modifications to gravity itself. In classical oscillating models derived from Einstein's equations, the critical parameter is the total energy density of the universe. If that density exceeds a certain threshold, gravity's pull would eventually overcome the outward momentum of expansion, halting it and reversing the motion. This reversal would lead to a contraction phase culminating in a big crunch. The big crunch, in turn, could lead to another big bang, starting the next cycle. But, as mentioned earlier, the discovery of cosmic acceleration and dark energy upended the simplicity of this picture. In a universe dominated by dark energy with a constant density, expansion would never reverse. It would continue indefinitely, preventing a new cycle from starting. To circumvent this, some modern cyclic models propose that dark energy itself evolves over time, perhaps oscillating in its properties. In these scenarios, the repulsive effect of dark energy could weaken and eventually reverse, allowing gravity to regain dominance and initiate contraction. The behavior of such a dynamical dark energy field is often described in terms of a scalar field rolling along a potential landscape, gaining and losing energy in a way that could drive both expansion and contraction phases. One influential modern framework that incorporates these ideas is the cyclic model developed by Paul Steinhardt and Neil Turok. Building on the ekpyrotic scenario from string theory, they propose that our universe is a three-dimensional brain moving through a higher dimensional space, periodically colliding with another brain. Each collision is experienced as a big bang in our universe, producing hot, dense conditions that eventually cool into the structures we observe. Between collisions, the universe undergoes a long, slow contraction that smooths and flattens it, ensuring that each new expansion starts from conditions consistent with current observations. The Steinhardt-Turok model has an elegant answer to the entropy problem. During the expansion phase, entropy is diluted by the accelerated expansion caused by dark energy, pushing most of it beyond the observable horizon. Then, during the slow contraction, the universe is smoothed out without significantly increasing entropy in the region that will become our observable universe in the next cycle. This mechanism, while mathematically plausible, is challenging to test directly, as it relies on processes that occur in epochs far removed from our observational reach. Another intriguing variant comes from loop quantum cosmology, which modifies the behavior of gravity at extremely high densities. In this framework, quantum effects create a repulsive force that becomes dominant, when matter and energy densities approach the Planck scale, preventing the formation of singularities. Instead of a big crunch singularity, the universe undergoes a bounce at a finite density, rebounding into a new expansion phase. Loop quantum cosmology predicts that such bounces could occur repeatedly, allowing for an eternal sequence of universes without a singular beginning or end. What distinguishes loop quantum cosmology from other cyclic models is that it emerges naturally from an attempt to quantize gravity rather than being designed specifically to produce cycles. This makes it appealing to some physicists because it ties the fate and origin of the universe directly to deeper questions about the nature of space-time. Moreover, it offers testable predictions in principle, such as specific patterns in the cosmic microwave background that could reveal traces of a pre-bounce universe. Despite their differences, all cyclic models must contend with the same observational constraints. They must explain why the universe is so flat and homogeneous on large scales, why the cosmic microwave background has the statistical properties it does, and why the distribution of galaxies and clusters matches what we see. They must also be consistent with the measured value of dark energy today, and with its apparent constancy over billions of years. Balancing these requirements while still allowing for cycles is a delicate task. One of the most difficult aspects of testing cyclic theories is that the evidence for prior cycles may be extremely faint or erased altogether. If each bounce truly resets the universe, then direct physical relics from previous cycles may be impossible to detect. This does not mean they leave no trace, but the traces might be statistical or subtle. Slight anomalies in the cosmic microwave background, unusual correlations in large-scale structure, or perhaps a gravitational wave background with a unique signature. These challenges have not deterred theorists from refining and expanding cyclic ideas. In fact, the search for observational fingerprints of a pre-Big Bang universe is an active area of research. Some scientists are investigating whether certain anomalies in the Planck satellite's map of the cosmic microwave background, such as the so-called cold spot, could be remnants from a prior cycle. Others are studying how future gravitational wave detectors could pick up signals from processes that occurred before the last bounce. Cyclic models also intersect with philosophical questions about time and causality. If cycles have been occurring forever, is there a meaningful sense in which one can speak of a first cause? Or is the chain of events truly infinite, with no need for an ultimate explanation? For some, the idea of an endless chain is unsatisfactory, pushing the mystery of existence back without resolving it. For others, it is a perfectly acceptable endpoint, replacing a singular beginning with an eternal process. While we may never be able to witness a full cycle, our current moment in the cosmic story may still hold clues about the larger pattern. Just as geologists infer the cycles of Earth's climate from ice cores and sediment layers, cosmologists may one day piece together the cycles of the universe from the faint imprints left on the oldest light and the deepest structures in space. One of the most striking aspects of cyclic cosmology is how it forces us to rethink the nature of cosmic evolution. In the standard Big Bang model, the universe evolves along a single trajectory, from an initial hot, dense state through cooling and structure formation toward an eventual fate determined by its energy content. In a cyclic model, however, the fate is never final. Each end contains the seed of a new beginning. This dramatically changes the way we view cosmological history. Rather than a straight line with a start and an endpoint, cosmic history becomes an endless loop, with each cycle having its own expansion, structure formation, and eventual contraction or transformation. This framework allows for interesting possibilities when it comes to the diversity of cosmic conditions. While some cyclic models propose that every cycle is nearly identical, producing universes with similar physical laws and constants, others allow for variation. Small changes in initial conditions after each bounce could lead to slightly different universes, potentially with altered particle masses, strengths of fundamental forces, or even entirely different physical laws. Over infinite time, such variations could result in an immense landscape of universes, each with its own characteristics, some capable of supporting life, others not. The idea of variation between cycles connects cyclic cosmology to aspects of the anthropic principle, If the constants of our universe seem finely tuned for the emergence of complex structures and life, one possible explanation is that we are simply in one of many cycles, perhaps one of the rare ones, with parameters that happen to permit observers like us. In this sense, cyclic models offer an alternative to multiverse theories arising from eternal inflation, replacing spatial diversity with temporal diversity. Instead of countless universes existing simultaneously, countless universes exist sequentially. Another rich area of discussion is the potential role of black holes in a cyclic universe. In conventional cosmology, black holes are often seen as endpoints for matter, trapping it beyond their event horizons. But in some speculative scenarios, the interiors of black holes might connect to other regions of spacetime, or even seed new universes. In a cyclic framework, black holes could play a role in transferring information, matter, or energy between cycles, although such ideas remain highly speculative and face serious theoretical challenges. When considering the observational consequences of cyclic models, one of the key targets is the cosmic microwave background, CMB. Because the CMB is the oldest light we can observe, it carries information from the early universe, and potentially from conditions that existed before our current expansion. In cyclic scenarios, subtle imprints from a previous contraction or bounce might survive in the statistical distribution of temperature fluctuations in the CMB. For example, certain patterns of non-Gaussianity, or unexpected correlations between fluctuations at different scales, could be telltale signs of a pre-Big Bang phase. Some proponents of cyclic cosmology have suggested that specific anomalies in the CMB, such as low power regions at large angular scales, or the alignment of certain multipoles, might be relics from before the last bounce. These claims are controversial, as such anomalies could also arise from statistical noise or other astrophysical effects. Nonetheless, the possibility that our universe's oldest light contains echoes of a previous cycle is a tantalizing motivation for further investigation. Gravitational waves offer another potential observational window. Unlike light, gravitational waves interact very weakly with matter, allowing them to travel across the universe almost unimpeded. This makes them excellent messengers from the earliest moments of cosmic history. If a prior cycle ended in a bounce, the violent dynamics of that event could have produced a distinctive gravitational wave background. Future detectors, both ground-based and space-based, may be sensitive enough to detect such a background, providing a rare glimpse into epochs beyond the reach of electromagnetic observations. One question that arises naturally in cyclic cosmology is whether cycles are truly infinite in both directions, or whether they have a starting point. While the whole point of these models is to avoid a beginning, certain mathematical analyses suggest that there could still be an initial cycle in the distant past, after which the process became eternal. Whether or not this initial cycle exists depends on the details of the model, especially the behavior of entropy, dark energy, and the fundamental structure of space-time. The presence of infinite cycles also raises philosophical and probabilistic puzzles. If there have been an infinite number of cycles before ours, then anything that could happen, no matter how unlikely, should have happened infinitely many times already. This includes configurations identical to our current universe. This raises questions about the uniqueness of our cosmic moment. Are we living in a cycle that is truly special, or simply one of countless near-identical repetitions? While such questions may never be answerable in a strict scientific sense, they highlight the profound implications of adopting an eternal cyclic framework. It is also worth noting that cyclic models need not be perfectly regular. While the term cycle suggests repetition, the actual length, size, and conditions of each cycle could vary depending on the dynamics at play. For instance, changes in the properties of dark energy, variations in scalar field potentials, or the influence of quantum effects during bounces could all cause cycles to differ from one another. This variability could, in principle, leave a signature in the large-scale structure of the universe, or in subtle shifts in cosmological parameters over time. Ultimately, the cyclic view of the universe is as much a philosophical stance as it is a scientific hypothesis. It replaces the finality of a single creation event with the notion of eternal renewal, offering a cosmos that is self-contained and self-sustaining. While we lack definitive evidence for such a process, The framework's ability to address the question of origins without invoking a singular beginning ensures it remains an active area of exploration. The combination of aesthetic elegance, theoretical plausibility, and the possibility, however remote, of observational confirmation makes the cyclic universe one of the most fascinating alternatives to the standard cosmological model. If the cyclic universe concept is correct, then our current cosmic era is only a small act in an unimaginably long performance. This perspective has profound implications not only for cosmology, but also for our place within it. In a linear model with a beginning and an end, our moment in time can feel uniquely significant, a brief flash between two great unknowns. In an eternal cyclic model, however, our existence is woven into an unending tapestry where beginnings and endings are relative, not absolute. Life, planets, and galaxies may come and go, but the process that gives rise to them continues without interruption. One of the key philosophical shifts in this view is that creation is no longer a singular event, but a continuous feature of reality. In each cycle, conditions emerge that allow complexity to form, whether that complexity takes the form of stars, biological organisms, or something entirely beyond our current understanding. This ongoing generative process sidesteps the need to explain how the universe came into being from nothing. Instead, it focuses on the mechanisms that sustain its perpetual renewal. From a scientific standpoint, the success of the cyclic model depends on its ability to match observations as precisely as the standard Big Bang plus inflation framework. The challenge is that inflation has been extremely successful at explaining the flatness, uniformity, and structure of the observable universe. Any alternative model, including cyclic cosmology, must reproduce these results without the same inflationary assumptions, or incorporate its own version of inflation in a way that is consistent with cycles. This is why many modern cyclic scenarios, such as the ekpyrotic model, devote so much attention to explaining how the smoothing and flattening of the cosmos occurred during the contraction phase. A further challenge is explaining the arrow of time. In thermodynamics, the arrow of time is associated with the increase of entropy. In a cyclic model, if entropy truly increases in each cycle, then either the cycles must become progressively larger to accommodate the extra entropy, or there must be a mechanism that reduces or disperses it between cycles. This remains one of the most actively debated issues in the field. Some proposals suggest that the accelerated expansion during each cycle could push high entropy regions beyond the observable universe, effectively resetting the clock for the next cycle. Others explore more exotic ideas, such as entropy recycling through quantum gravitational processes. Another consideration is the fate of information. In a standard cosmological scenario with an ultimate end, such as a heat death or a big rip, information about the universe's past could be irretrievably lost. In a cyclic universe, the question is more complicated. If the cycles are perfectly regular and deterministic, information might, in principle, be preserved in some form, though it could be scrambled beyond recognition. If the cycles vary, then information about past cycles might be erased altogether. Understanding the behavior of information in cyclic cosmology could have deep connections to the unresolved information paradox in black hole physics. While much of the current work on cyclic universes is highly mathematical and abstract, the motivation for pursuing these ideas is rooted in some of the oldest questions humanity has asked. Myths of eternal return, cosmic renewal, and cycles of death and rebirth appear in cultures across the globe, from the Hindu Kalpas to the Norse Ragnarok and the Stoic ekpyrosis. The modern scientific version strips away the mythological characters, but retains the core intuition that the universe is not a one-time event, but a recurring process. Testing these ideas will require advances in observational astronomy and theoretical physics. More sensitive measurements of the cosmic microwave background, especially of its polarization patterns, could reveal signatures of a pre-Big Bang phase. The detection of a primordial gravitational wave background would be another critical milestone, as certain cyclic models predict distinctive features in such a signal. Surveys of large-scale cosmic structure could also help, by checking whether the distribution of galaxies contains imprints from earlier cycles. Even if these observations ultimately favor the standard inflationary model over a cyclic alternative, the effort to explore cycles will not have been wasted. In science, pursuing alternative hypotheses sharpens our understanding of the dominant paradigm and ensures that our theories remain grounded in testable predictions rather than unquestioned assumptions. Moreover, cyclic models often push theoretical physics into new territory, inspiring novel approaches to problems in quantum gravity, dark energy, and cosmological initial conditions. In the grand scheme, the cyclic universe stands as both a challenge and an invitation. It challenges the prevailing view that time has a beginning and perhaps an end, replacing it with a vision of perpetual transformation. And it invites us to imagine a reality in which everything we know is part of an infinite chain of events, stretching endlessly backward and forward, with no ultimate origin or conclusion. Whether or not future evidence supports this vision, it reminds us that the universe may be far stranger and more intricate than the simple story of a single Big Bang. For now, the cyclic model remains a possibility, one that cannot yet claim victory, but also refuses to be ruled out. It persists because it offers a coherent, if unconventional, answer to one of the most profound questions we can ask. Has the universe always been here? If the answer is yes, then we live not in the first universe nor the last, but in one of countless cycles, each a verse in an eternal cosmic poem whose beginning and ending are forever beyond our grasp. The steady-state theory. Among the alternative visions of a universe without a beginning, the steady-state theory holds a special place in the history of cosmology. In the mid-20th century, it stood as the primary rival to the Big Bang model, offering an elegant, philosophically appealing picture of a cosmos that looks the same at all times on the largest scales. While the steady-state theory has since fallen out of favor due to overwhelming observational evidence against it, the ideas it introduced remain important for understanding how scientists think about the possibility of an eternal universe. The core principle of the steady-state theory is called the perfect cosmological principle. The ordinary cosmological principle, still accepted today, states that on sufficiently large scales, the universe is homogeneous and isotropic. It looks roughly the same in all directions and from all locations. The perfect cosmological principle goes further, claiming that the universe is also homogeneous in time. That is, its large-scale appearance and properties do not change as the ages pass. Galaxies may move, stars may be born and die, but the overall density of matter and the structure of the cosmos remain constant. This principle implies that the universe has no beginning or end. It has always existed in its present form and will continue to do so forever. In the late 1940s, 3 British astronomers, Hermann Bondi, Thomas Gold, and Fred Hoyle, independently developed and refined the steady-state model. They were motivated in part by philosophical concerns about the notion of a cosmic origin. The Big Bang, as it was coming to be called, seemed to them to introduce an arbitrary moment of creation without a clear physical mechanism. By contrast, the steady-state theory provided a timeless, self-sustaining universe in which the laws of physics operated eternally without requiring a special beginning. To make the model work, its proponents had to explain how the universe could be expanding, as Edwin Hubble's observations of galaxy redshifts had shown, while still maintaining a constant density of matter. The solution was to propose that new matter is continuously created out of the vacuum at just the right rate to balance the dilution caused by expansion. This process would be extremely slow, about 1 hydrogen atom per cubic meter per billion years, but over cosmic distances and timescales, it would be enough to keep the density constant. The idea was that as galaxies moved apart, new material would gradually appear in the gaps, eventually forming new stars and galaxies to replace those that moved out of view. This concept of continuous creation was not entirely ad hoc. It drew on certain interpretations of quantum theory, in which particles can spontaneously appear from fluctuations in a field. However, in the steady-state model, the creation process was postulated as a new law of nature, operating uniformly throughout space and time. The creation field responsible for this was sometimes referred to as the C field in Hoyle's work, a hypothetical field with negative energy density that could generate matter without violating conservation laws, when the entire system, including gravitational effects, was considered. One of the appealing features of the steady-state theory was its simplicity. By asserting that the universe is unchanging in its large-scale properties, it eliminated the need to explain initial conditions or early-time evolution. There was no horizon problem because the universe had always been in a steady state. There was no need for inflation or other mechanisms to explain large-scale uniformity. Moreover, the model made clear, testable predictions. The statistical properties of galaxies, quasars, and other cosmic structures should remain the same at all epochs, and the number density of galaxies should be constant over time. For about 2 decades, the steady-state theory enjoyed considerable support, particularly among astronomers who were skeptical of the idea of a beginning. Fred Hoyle, in particular, was a vocal advocate and a formidable public defender of the model. He famously coined the term Big Bang during a BBC radio broadcast, intending it as a somewhat dismissive nickname for the rival theory. Ironically, the name stuck and is now universally used. Even by supporters of the model, it was meant to criticize. However, as astronomical techniques improved in the 1950s and 1960s, evidence began to mount against the steady-state model. One of the first challenges came from radio astronomy, which revealed that the population of distant radio galaxies was not the same as that of nearby ones. In the steady-state picture, the statistical properties of the universe should be constant over time, so there should be no difference in the types or numbers of galaxies at different redshifts. But observations showed that distant regions, corresponding to earlier times in the universe, contained more radio-loud and irregular galaxies than the nearby universe. This suggested that the cosmos does change over time, contradicting the perfect cosmological principle. The decisive blow to the steady-state theory came in 1965 with the discovery of the cosmic microwave background radiation, CMB, by Arno Penzias and Robert Wilson. This faint glow of microwaves, coming from all directions, was quickly recognized as the afterglow of a hot, dense early phase of the universe, exactly what the Big Bang model predicted. The steady-state theory, by contrast, had no natural explanation for such radiation. Attempts to account for it within the steady-state framework were forced and unconvincing, relying on speculative sources like scattered starlight or intergalactic dust, which failed to match the observed spectrum of the CMB. By the late 1960s, the steady-state theory had lost most of its adherents in the scientific community. Observations of galaxy evolution, quasar populations, and the detailed properties of the CMB all supported the Big Bang model over the steady state. Yet the steady-state theory remains an important case study in the history of science because it shows how a bold, simple hypothesis can capture the imagination, make clear predictions, and ultimately be tested and rejected by empirical evidence. Even in defeat, the steady-state idea influenced later thinking about the cosmos. The notion of continuous creation of matter, for instance, has conceptual parallels in modern models involving quantum fields and vacuum fluctuations. And the philosophical attraction of a timeless universe has never entirely disappeared, resurfacing in modified or hybrid models that attempt to preserve some aspects of the steady state while incorporating the evidence for cosmic evolution. Even after the mainstream scientific community had moved away from the steady-state theory, its core philosophical appeal continued to resonate. The idea of a universe that is eternal and unchanging on the largest scales fits naturally with certain philosophical and even aesthetic preferences. It removes the need to grapple with a singular creation event and the associated question of what, if anything, came before. In a steady-state cosmos, there is no before in an absolute sense. Time stretches endlessly in both directions, and the same broad patterns persist forever. Fred Hoyle and a few collaborators continued to refine the steady-state model in the years following its decline in popularity. They explored variations that could account for some of the observational challenges without abandoning the central principle of temporal homogeneity. One such variant was the quasi-steady-state cosmology, developed in the 1990s by Hoyle, Jeffrey Burbidge, and Jayant Narlikar. This model retained the concept of continuous matter creation, but allowed for periodic episodes of enhanced creation activity, leading to modest fluctuations in the density and distribution of matter over time. In the quasi-steady state model, the universe is still eternal, but rather than being perfectly static in its large-scale appearance, it undergoes gentle oscillations in density and temperature over extremely long timescales, on the order of tens of billions of years. These oscillations could, in principle, explain certain observed features of galaxy distribution, and might even mimic aspects of Big Bang cosmology without invoking an initial singularity. However, the model still faced serious difficulties explaining the cosmic microwave background. Its proponents suggested alternative origins for the CMB, such as thermalized starlight or radiation from mini Big Bangs, associated with creation events. But these explanations could not match the precision of the Big Bang model's predictions for the CMB's nearly perfect blackbody spectrum. Another challenge for the steady-state and quasi-steady state theories was the increasingly detailed study of cosmic chemical evolution. Observations revealed that the abundance of light elements like helium, deuterium, and lithium match the predictions of the Big Bang nucleosynthesis, a process that would have occurred in the hot, dense early universe. The steady-state model could not naturally produce these abundances without invoking processes that seemed ad hoc and lacked independent justification. As a result, the chemical evidence further reinforced the Big Bang framework. Despite these setbacks, the steady-state perspective continues to serve as a valuable intellectual counterpoint in cosmology. It reminds scientists of the importance of considering alternative frameworks and of the dangers of assuming that a prevailing theory is the only possible explanation. In some respects, the steady-state idea anticipated modern discussions about the multiverse and eternal inflation. For example, in eternal inflation scenarios, the large-scale structure of reality does not change in its statistical properties over time. New pocket universes are constantly being created in an inflating background, somewhat analogous to the continuous creation of matter in the steady-state model. Philosophically, the steady-state theory also keeps alive the discussion about whether the universe must have a beginning. Even though the observational evidence strongly favors a finite age for our observable universe, it remains possible that the larger cosmos has existed forever. Some theorists consider the Big Bang to be a local event, perhaps one of many in a vast eternal spacetime, rather than the absolute origin of everything. In this way, the steady-state vision finds a kind of partial echo in certain speculative modern models. One interesting legacy of the steady-state approach is its emphasis on elegance and simplicity in theory building. By positing a small number of principles, the perfect cosmological principle and continuous creation, the model sought to explain the universe without introducing special initial conditions. This drive for simplicity continues to guide much of theoretical physics. Even when the specifics of the steady-state model are set aside, the idea that the laws of nature should be the same everywhere and every when remains a powerful guiding assumption, though one that is now balanced against the recognition that the universe does, in fact, evolve over time. The public and cultural impact of the steady-state theory should not be underestimated either. In the mid-20th century, the debate between steady-state and Big Bang cosmology was widely covered in newspapers, magazines, and radio broadcasts. It was one of the first times that a fundamental question about the nature of the universe, its origin or lack thereof, became part of popular discourse in a sustained way. Fred Hoyle, with his sharp wit and media presence, played a major role in bringing cosmology to the public, even if his preferred theory ultimately lost out. The term Big Bang, originally coined somewhat derisively, became a household phrase and an enduring reminder of that era's scientific controversies. In the classroom, the steady-state theory is often presented today as a cautionary tale, a vivid example of how scientific theories must stand up to empirical testing. Its clear, falsifiable predictions were a strength, not a weakness, because they allowed the model to be decisively ruled out when the evidence failed to support it. This stands in contrast to vague or unfalsifiable ideas, which can linger indefinitely without making progress. In this way, the steady-state theory's failure was a triumph of the scientific method. At the same time, some historians of science caution against viewing the steady-state theory as merely a failed idea. They point out that its development spurred major observational campaigns, particularly in radio astronomy, that enriched cosmology as a whole. The need to distinguish between steady state and Big Bang predictions drove the collection of deep sky surveys, redshift catalogs, and radio source counts, many of which provided data that remain valuable today. Thus, the competition between the two models advanced the field even as it resolved the central debate. In modern cosmology, direct descendants of the steady-state theory are rare, but the philosophical motivation behind it persists. The desire for an eternal, unchanging cosmos continues to inspire certain theoretical explorations, especially in the context of quantum gravity and high-energy physics. Whether these efforts will produce a viable alternative to the Big Bang, or whether they will meet the same observational fate as the original steady state, remains to be seen. What is certain is that the steady-state theory will remain a landmark chapter in the story of cosmology, a reminder that even elegant, appealing ideas must ultimately yield to the verdict of nature. When we consider the steady-state theory in the broader context of cosmological thought, it occupies a unique place as both a bold hypothesis and a philosophical statement. It was bold because it dared to propose a radically simple framework for the universe, one that was in stark contrast to the emerging Big Bang paradigm. And it was philosophical because it was built on a principle that was more aesthetic than empirical. The perfect cosmological principle, while mathematically straightforward, reflected a human preference for symmetry, uniformity, and permanence. In some sense, it was a vision of the cosmos that mirrored the unchanging heavens, as imagined by many ancient cultures. One reason the steady-state theory initially gained traction was the lack of detailed observational data in the late 1940s and early 1950s. At that time, the large-scale structure of the universe was still poorly understood, and the discovery of cosmic acceleration was decades away. In this relatively open landscape, competing models could coexist without immediate contradiction. The steady-state theory seemed no more implausible than the Big Bang, and in some ways it appeared more philosophically satisfying because it avoided the conceptual difficulties of a cosmic origin. It is important to recognize that the theory did make concrete, testable predictions, something that distinguishes it from many purely philosophical speculations. For example, it predicted that the distribution of galaxies would be statistically the same at all redshifts, that the universe's density would remain constant over time, and that there would be no observable relic radiation from a hot, dense phase. These predictions allowed it to be tested directly, and ultimately, to be ruled out. The process by which the steady-state theory fell out of favor illustrates the self-correcting nature of science. The theory was not abandoned because of a sudden shift in philosophical taste, but because increasingly precise observations contradicted its core predictions. The discovery of the CMB was particularly damaging, not only because the steady-state model could not explain it naturally, but because the Big Bang model had predicted it decades earlier. In the work of George Gamow, Ralph Alpher, and Robert Herman, this predictive success gave the Big Bang framework a decisive advantage. Another decisive line of evidence came from the study of galaxy evolution. Deep sky surveys showed that galaxies in the distant past, and thus seen at earlier cosmic times, were different in morphology and activity compared to nearby galaxies. There were more irregular and actively star-forming galaxies in the early universe, and quasars, extremely luminous active galactic nuclei, were far more common billions of years ago than they are today. This clear evidence of cosmic evolution could not be reconciled with the steady-state assertion that the large-scale properties of the universe do not change with time. Even so, the steady-state theory did not disappear instantly. A small group of dedicated proponents continued to explore modifications and refinements. One avenue was to consider hybrid models in which certain large-scale statistical properties remained constant, but local regions could evolve. These ideas anticipated, in a way, the more recent multiverse scenarios in which our observable universe is just one region within a much larger, possibly eternal structure. In both cases, the larger framework can remain statistically steady, even while local patches undergo dynamic change. The legacy of the steady-state theory also extends into the realm of science communication. Fred Hoyle, in particular, was an effective and charismatic popularizer of science, and his public defense of the steady state, along with his many other contributions to astrophysics, such as the theory of stellar nucleosynthesis helped bring cosmology into mainstream awareness. The public debate between steady-state and Big Bang cosmology was one of the first instances in which a deep scientific question about the universe's origin was widely discussed outside of academia. In retrospect, one can see the steady-state theory as part of a continuum of attempts to reconcile our observations of the cosmos with our philosophical intuitions. For centuries, many thinkers assumed the universe was eternal and unchanging because that view seemed natural and aligned with everyday experience. The steady-state model was a modern scientific expression of this timeless intuition. Its eventual failure reminds us that the universe does not exist to satisfy our aesthetic preferences. It is what it is, regardless of whether we find its story neat or comforting. Interestingly, the steady-state theory has experienced something of a conceptual afterlife in certain speculative domains of theoretical physics. Ideas about cosmic inflation, the multiverse, and eternal inflation all share with steady-state cosmology the notion of a larger reality that remains statistically the same over vast spans of time, even if local conditions vary. In eternal inflation, for example, new pocket universes are constantly forming within an inflating background, leading to a steady-state-like situation at the largest scales. While the physics driving this process is very different from the matter creation mechanism of the original steady-state theory, the philosophical implication, a universe with no true beginning or end, is strikingly similar. There is also a broader methodological lesson to be drawn from the rise and fall of the steady state. Scientific theories must be judged not only by their internal consistency and elegance, but by their ability to make falsifiable predictions and to withstand the scrutiny of observation. The steady-state theory excelled at the first two criteria, but failed at the third. This does not diminish its intellectual value. Indeed, its clear predictions made it easier to test and ultimately to replace with a model better supported by evidence. The willingness of its proponents to engage in open, evidence-based debate is a model for scientific discourse. Hoyle, Bondi, and Gold did not retreat into dogma when their theory was challenged. They argued their case vigorously, sought new evidence, and revised their ideas in response to data. While they were ultimately on the losing side of the debate, their work helped sharpen the questions that cosmology needed to answer, and their methods enriched the field. Today, the steady-state theory is primarily encountered in textbooks and histories of science as a classic example of how empirical data can overturn even the most elegant theoretical constructions. But it is more than just a cautionary tale. It is a reminder that the universe can surprise us, that our intuitions about how it should be may not align with how it actually is, and that the path to understanding is paved with both successes and failures. By the time the steady-state theory was largely set aside in favor of the Big Bang model, cosmology had entered a new era, one in which increasingly precise observations allowed for the testing of ideas at a level unimaginable in the mid-20th century. Yet even in its defeat, the steady-state theory continued to influence how cosmologists approach the great questions of origin, structure, and fate. Its commitment to a simple guiding principle, its insistence on testability, and its willingness to make bold predictions all left an enduring mark on the field. One of the lasting contributions of the steady-state debate was the sharpening of observational cosmology as a discipline. In the 1950s and 1960s, astronomers began building the infrastructure needed to measure the distribution of galaxies, the properties of distant radio sources, and the detailed behavior of cosmic radiation. These efforts, while motivated in part by the desire to distinguish between the steady-state and Big Bang models, laid the groundwork for the modern precision cosmology we know today. The deep sky surveys, high-sensitivity radio telescopes, and eventually space-based observatories that emerged from this period have since been used to answer questions far beyond the original debate. The steady-state theory also played an important role in shaping how physicists and astronomers thought about the role of creation in cosmology. By proposing that matter could be continuously created at a low but steady rate, Hoyle and his colleagues challenged the assumption that conservation of mass energy was an inviolable principle on cosmological scales. While the specific mechanism they proposed, the hypothetical C field, has not been supported by evidence, The idea that the laws of physics might operate differently at the largest scales has persisted in various forms. In certain modern models, for example, dark energy is treated as a dynamic field whose properties evolve over time, echoing the speculative boldness of the steady-state era. In a broader cultural sense, the steady-state theory also serves as a reminder that scientific ideas do not exist in isolation from the philosophical climate in which they arise. Post-war optimism, a fascination with permanence, and a desire to see the universe as fundamentally stable all contributed to the theory's appeal in the late 1940s. Similarly, the eventual embrace of the Big Bang was aided by a growing willingness to accept a dynamic, evolving universe, a view that fit well with the broader mid-century understanding of change and progress in other fields, from geology to biology. Although the steady-state model failed to match the evidence, its intellectual DNA can still be found in certain contemporary ideas. The concept of large-scale statistical uniformity reappears in eternal inflation and some versions of the multiverse. The notion that the cosmos may be infinitely old remains viable in specific frameworks, such as certain bouncing or emergent universe models. In this sense, the steady-state theory did not vanish completely. It was transformed, its central themes reinterpreted in new theoretical languages. The story of the steady-state theory also underscores an important truth about the scientific method. Being wrong is not the end of the road. A theory can be wrong in its details, but still profoundly useful in advancing understanding. The steady-state model encouraged astronomers to think more deeply about the relationship between theory and observation, about how to construct models that are both elegant and falsifiable, and about the importance of looking for phenomena that could definitively prove or disprove a hypothesis. In teaching cosmology today, the steady-state theory offers instructors a rich example of how science works in practice. Students can see how a theory begins with a clear philosophical premise, is formalized mathematically, makes testable predictions, and is subjected to rigorous empirical tests. They can also see how new data, whether in the form of radio source counts, galaxy surveys, or the cosmic microwave background, can decisively shift the consensus. In this way, the theory's rise and fall is not just a historical episode, but a living lesson in scientific reasoning. Even in popular culture, echoes of the steady-state vision remain. The idea of a universe without beginning or end continues to appear in literature, film, and art, often as a backdrop for exploring themes of immortality, recurrence, and the cyclical nature of existence. While these depictions rarely reflect the precise details of the scientific theory, they carry forward its most alluring aspect, the vision of a cosmos that has always been here and always will be. In the final analysis, the steady-state theory's greatest gift to cosmology may have been its boldness. By standing as a credible alternative to the Big Bang for nearly 2 decades, it forced scientists to refine their models, improve their instruments, and seek out ever more precise data. It demonstrated that in science, competition between theories is not only healthy, but essential, driving the field toward deeper understanding. And it reminded us that the universe often resists our attempts to impose simplicity, requiring us instead to follow the evidence wherever it leads. The steady-state theory may no longer describe our universe, but it remains a vital chapter in the ongoing story of humanity's attempt to comprehend the cosmos. In its insistence on an eternal, unchanging universe, it offered a profound, if ultimately incorrect, answer to one of the oldest questions we can ask. Has the universe always been here? While the current answer points to a finite age and a hot, dense beginning, the steady-state vision ensures that the question will continue to be asked, and that alternative possibilities will always be part of the conversation. Quantum and multiverse models of no beginning. When cosmologists attempt to describe a universe without a beginning, some of the most daring and conceptually challenging ideas come from the intersection of quantum theory and the concept of the multiverse. Classical cosmology, based on Einstein's general relativity, treats space-time as a continuous fabric with a well-defined geometry. But when we push our theories back to the extreme conditions near the supposed beginning of the universe, this smooth description breaks down. Quantum effects, fluctuations, uncertainties, and the probabilistic nature of reality become dominant. and the very notion of a singular first moment may lose meaning entirely. Quantum cosmology seeks to merge the insights of quantum mechanics with the large-scale structure of space-time described by general relativity. This is not an easy marriage. The two theories are famously incompatible in their current forms. Quantum mechanics excels at describing the behavior of subatomic particles and their interactions, while general relativity is unmatched in explaining gravity and the dynamics of stars, galaxies, and the cosmos as a whole. But near the Planck scale, about 10 to the negative 35th meters, both sets of laws must operate simultaneously, and neither theory on its own is sufficient. In this regime, entirely new physics is expected to emerge, potentially replacing the notion of a beginning with something radically different. One influential approach in quantum cosmology is the Hartley-Hawking no-boundary proposal, developed by James Hartle and Stephen Hawking in the early 1980s. This idea treats the universe's history as finite, but without a sharp edge in time, similar to how the surface of a sphere has finite area, but no boundary. In this model, as we go back toward what would normally be called the beginning, time gradually transforms into a spatial dimension. There is no singular moment where time simply starts. Instead, the geometry of space-time closes smoothly. In this sense, the question, what happened before the Big Bang, is like asking, what's north of the North Pole? It presupposes a boundary that doesn't exist. Another prominent idea comes from loop quantum cosmology, LQC, which applies the principles of loop quantum gravity to the entire universe. In LQC, space-time itself is quantized, meaning it has a discrete structure at the smallest scales. This discretization changes the behavior of gravity at extremely high densities, introducing a repulsive force that prevents singularities. In place of a Big Bang, the equations predict a big bounce. The universe contracts to a minimum but finite size and then expands again. If this process has been happening forever, with each bounce leading to a new phase of expansion, then the universe could be eternal in both directions of time. The bounce scenario has a particular appeal because it replaces the infinite densities of the singularity with finite, calculable quantities, allowing physicists to make more well-defined predictions. Moreover, if traces of the pre-bounce universe survive the transition, they might be detectable in the cosmic microwave background or in patterns of primordial gravitational waves. This makes the bounce not just a philosophical alternative to a beginning, but a potentially testable hypothesis. The multiverse concept adds another layer to the picture. In its simplest form, the multiverse is the idea that our observable universe is just one region in a much larger and possibly infinite cosmos. These regions, sometimes called pocket universes, can have different physical laws, constants, and histories. The multiverse can arise in various ways, but one of the most studied mechanisms is eternal inflation. In this scenario, inflation, the rapid exponential expansion thought to have occurred in the very early universe, is not a one-time event. Instead, it continues indefinitely in most regions of space, with occasional bubble nucleations, where inflation ends and a hot Big Bang phase begins. Each bubble is effectively its own universe, with its own finite age, but the overall multiverse has no beginning. Eternal inflation avoids the problem of a singular start by embedding our universe's beginning within a larger, timeless process. While our particular bubble has an origin, the inflating background does not. It has been generating bubbles forever and will continue to do so indefinitely. This raises the intriguing possibility that our universe is neither the first nor the last of its kind, but simply one among an endless population of universes. Quantum theory plays a crucial role in eternal inflation because the process of bubble nucleation is driven by quantum fluctuations in the inflaton field, the hypothetical field responsible for inflation. These fluctuations can cause different regions of space to exit inflation at different times, creating a patchwork of universes with varying properties. In some versions of the theory, the set of possible universes is vast enough to include every physically consistent configuration, making the multiverse a cosmic realization of all that is possible. There are also quantum cosmological models in which the universe exists in a timeless state, described by a wave function. In this view, what we perceive as time and evolution is an emergent phenomenon, arising only when certain conditions are met. One such approach uses the Wheeler-DeWitt equation, a central equation in canonical quantum gravity, which describes the quantum state of the entire universe without reference to time as an independent parameter. If time is emergent rather than fundamental, then the notion of a first moment may be meaningless. Our universe could simply be one configuration in an eternal, timeless quantum reality. Despite their differences, all of these quantum and multiverse models share a common feature. They remove the necessity for a singular, absolute beginning, whether through a bounce, a no-boundary geometry, an eternally inflating background, or a timeless quantum state. They replace the question, what happened at the start, with what larger framework gives rise to what we observe. This reframing shifts the focus from origins to mechanisms, from a fixed moment to an ongoing process. Of course, these ideas are extremely difficult to test. Observationally, we are confined to the finite region of space-time, accessible to our telescopes, limited by the speed of light and the age of the universe. Any evidence for pre-Big Bang phases, other universes, or timeless states must come indirectly through subtle signatures in the cosmic microwave background, gravitational waves, or the distribution of matter on the largest scales. The lack of direct access means that these theories must rely heavily on mathematical consistency, internal logic, and their ability to explain otherwise puzzling features of our universe. Even so, the appeal of quantum and multiverse models lies not just in their ability to potentially fit the data, but in their philosophical implications. They suggest a cosmos in which our universe is neither unique nor special in its existence, where the question, why is there something rather than nothing, may be answered not by a singular act of creation, but by the inevitability of existence in an eternal, self-sustaining system. One of the most fascinating aspects of quantum and multiverse models is how they challenge our intuitive understanding of causality. In everyday life, we experience events as chains of cause and effect, always with one thing leading to another. But in many of these models, causality is not fundamental, it is emergent. This means that, at the most basic level, the universe, or the multiverse, may not have a single starting point that caused everything else. Instead, what we perceive as a flow of time could arise from deeper, timeless structures, much as temperature arises from the motion of atoms without existing as a fundamental property of any single particle. In the Hartley-Hawking no-boundary proposal, for example, the beginning is replaced by a smooth geometry where time fades into a spatial dimension. In that regime, the conventional notion of cause and effect loses meaning because there is no before to cause an after. The early universe in this view does not emerge from a singularity, but from a region where the distinction between time and space simply doesn't exist. Once the universe grows large enough, time emerges as an approximate concept, and with it, the familiar patterns of causality. Loop quantum cosmology offers a different but related disruption of causality. In the bounce scenario, the contraction phase preceding our current expansion is governed by quantum gravitational effects that alter the standard rules of cause and effect. While from our perspective, the bounce is the start of everything we can observe, it may be just a transitional moment in a much larger sequence. The physics before and after the bounce are connected, but not in a simple linear fashion. Rather, they are joined by a quantum bridge where space-time behaves differently from anything we can experience directly. The multiverse picture introduces yet another twist. In eternal inflation, for example, new universes form constantly in an inflating background. Each one begins with its own Big Bang-like event, but the process of creating them has no global start. The inflating space may have existed forever, and because quantum fluctuations drive the creation of new universes, the chain of causes is distributed across space rather than anchored to a single moment. In some models, even the inflating background changes over time in complex ways, creating a dynamic but eternal environment in which universes come and go. One particularly intriguing implication of the multiverse is the possibility of vastly different physical laws in different universes. In eternal inflation, the properties of each bubble universe depend on the details of how inflation ends in that region, details that can vary due to quantum fluctuations in the inflatant field. This means that while our universe has the specific combination of forces, particles, and constants that allow for stars, planets, and life, other universes could have radically different configurations. From the standpoint of a no-beginning framework, there is no need for fine-tuning to occur in one single creation event. Given infinite time and infinite universes, every possible configuration will be realized somewhere. This ties into the anthropic principle, the idea that we observe the universe to be compatible with life because we could not exist to observe it otherwise. In a multiverse without beginning, the anthropic principle becomes a statistical inevitability. Out of the infinite variety of universes, some will have conditions that permit observers, and those are the universes in which observers will find themselves. While this reasoning does not explain why the multiverse exists in the first place, it reframes the apparent fine-tuning of our universe as a selection effect, rather than a deep cosmic mystery. Beyond eternal inflation, there are other multiverse models that connect directly to quantum mechanics. The many worlds interpretation of quantum mechanics, for instance, suggests that every quantum event leads to a branching of realities, with each possible outcome realized in its own branch. If applied to cosmology, this idea could mean that there is a vast, ever-growing collection of universes branching off from every possible quantum event. In such a framework, there is no single origin for all universes. They emerge continuously from the quantum substrate of reality. Another category of models proposes that the multiverse arises from cyclical or emergent processes. Some scenarios blend the bounce concept with the multiverse, envisioning each bounce as producing not just one universe but many. Others suggest that space-time itself could be a kind of emergent phenomenon arising from quantum entanglement patterns, meaning that the entire multiverse could be a manifestation of deeper, pre-space-time physics. In these approaches, the question of a beginning is replaced with the question of what fundamental structures give rise to both space and time. Testing these ideas is a monumental challenge. For the multiverse in particular, direct observation of other universes seems impossible, since by definition they are causally disconnected from ours. However, indirect evidence might still be possible. For example, if our universe had ever interacted with another, through a collision of bubble universes and eternal inflation, such an event could leave a subtle imprint in the cosmic microwave background. Researchers have proposed looking for circular patterns or other anomalies in the CMB that could be consistent with such collisions. So far, no definitive evidence has been found, but the search continues. Quantum cosmology models that predict a bounce may offer more concrete observational opportunities. If the pre-bounce universe left specific signatures in the spectrum of primordial gravitational waves or in the distribution of matter on the largest scales, we could, in principle, detect them with future instruments. The challenge is that the signals would be extremely faint and would have to be distinguished from other astrophysical processes. Still, even a small hint of a pre-Big Bang phase would have profound implications for our understanding of time and the possibility of a universe with no beginning. The deeper philosophical implication of these models is that the universe, or multiverse, may be better described as a self-contained system with no external cause. In classical thinking, we often imagine a chain of events that must have started somewhere, but in a quantum or multiverse framework, the chain might loop back on itself, or be infinite in extent, or dissolve entirely into a timeless backdrop. This shifts the focus from asking, what started it, to asking, what is the structure of the whole? The answer to that second question may be stranger and more beautiful than any single moment of creation could ever be. One of the most radical consequences of quantum and multiverse models of no beginning is that they allow for the possibility that our observable universe is just a small, transient patch in a far larger reality whose properties we can barely imagine. This larger reality may have existed forever, without a single point of origin, and may continue to exist forever, regardless of what happens to our local region. In this view, the familiar story of the Big Bang is not a story about the birth of everything, but simply the first chapter we can see in our own cosmic neighborhood. In eternal inflation, this neighborhood is one bubble among countless others. The process of bubble nucleation, driven by quantum fluctuations of the inflatant field, ensures that new universes are constantly being created in the inflating background. Some bubbles may be similar to ours, Others may be radically different, with alternate physics, dimensionalities, or even entirely different structures of space-time. If inflation has no beginning and no end, then this cosmic bubble bath has been ongoing forever. Each bubble has its own internal arrow of time, beginning at its own Big Bang, but the larger multiverse itself is timeless in the sense that it never started. In the no-boundary approach, the entire space-time of our universe is described by a wave function that contains all possible histories. These histories are weighted by their probabilities, and our observed universe is just one among many possible outcomes. In such a framework, it is meaningless to speak of a single, unique beginning. The concept of a sharp temporal boundary is replaced by a smooth quantum landscape in which time itself is a derived property. The origin of the universe becomes a feature of the mathematical description rather than a literal moment in time. Loop quantum cosmology's bounce scenario offers a more tangible visualization. In this picture, our current expanding universe was preceded by a contracting phase. As the contraction reached extremely high densities, quantum gravitational effects prevented a singularity, instead producing a bounce that launched the current expansion. The pre-bounce universe could have been very different from ours, with its own galaxies, stars, and perhaps even life. If the bounce process has occurred infinitely many times, then there is no first cycle, just an eternal sequence of expansions and contractions. This idea blends naturally with certain multiverse concepts, in which each bounce might lead to branching variations in physical laws. From a thermodynamic perspective, these scenarios raise deep questions about entropy. In our everyday experience, entropy increases over time, defining the arrow of time. If the universe has existed forever, what prevents entropy from reaching a maximum long ago, leaving a featureless, heat-dead cosmos? Some models solve this by proposing that the expansion of space can dilute entropy, pushing it beyond the observable horizon. Others suggest that new entropy is effectively reset or removed during certain phases, such as the bounce or the inflationary epoch. Still others challenge the universality of the second law of thermodynamics, suggesting that it might emerge only in certain regimes and not apply to the totality of reality. The philosophical implications are profound. In a universe or multiverse without a beginning, the why of existence is transformed. Rather than needing an external cause to bring the cosmos into being, existence simply is, a brute fact, without an ultimate explanation. This is conceptually challenging for many people, as it clashes with our deep-seated habit of seeking causes for every effect. Yet it also offers a form of closure. If reality has no origin, then the chain of "what caused this?" questions eventually stops, not with a cause, but with the acceptance that the chain itself is infinite or ill-defined. Some thinkers have even suggested that the no-beginning idea may help explain the apparent fine-tuning of our universe. In an eternal multiverse, every possible set of physical laws and constants will eventually occur, somewhere or somewhen. We find ourselves in a universe compatible with life, not because it was specially created for that purpose, but because in an infinite ensemble, such universes are inevitable. This anthropic reasoning is controversial. Critics argue that it lacks predictive power, but it does offer a naturalistic way to account for fine-tuning without invoking a one-time act of design. The search for empirical evidence of a no-beginning cosmos is ongoing, though it is hindered by the fact that much of the relevant physics occurs beyond our observational horizon. Still, there are strategies for testing certain aspects. For instance, collisions between bubble universes and eternal inflation could, in principle, leave subtle imprints in the cosmic microwave background. These might appear as circular or elliptical patterns of temperature variations that deviate from the statistical norms predicted by inflation alone. While searches for such patterns have so far yielded no conclusive detections, future, more sensitive surveys could improve the odds. Similarly, loop quantum cosmology predicts specific signatures in the spectrum of primordial gravitational waves, ripples in spacetime generated in the earliest moments of the universe. If these waves carry information from a pre-bounce phase, they could be detectable by next-generation gravitational wave observatories. Detecting such a signature would be a groundbreaking confirmation that our universe's expansion was preceded by a contraction. supporting the idea of an eternal sequence of cosmic epochs. Even the structure of quantum mechanics itself may offer indirect clues. If space-time emerges from deeper quantum entanglement patterns, as some researchers propose, then the universe's beginning could simply be a phase transition in these patterns, not an absolute start. In such a model, the laws of physics could evolve over infinite time, producing different regimes of reality without ever passing through a singular creation event. In the end, quantum and multiverse models of no beginning present a vision of reality that is vast, diverse, and fundamentally alien to our everyday intuitions. They invite us to imagine a cosmos in which time is not a straight arrow, but a tapestry of threads, some looping back on themselves, others stretching infinitely in both directions, all woven into a fabric that has no edge. It is a picture that challenges the very notion of a first cause and replaces it with the idea of an eternal framework in which universes, like waves on an endless sea, are constantly forming, evolving, and fading, with no beginning and no end. If we take quantum and multiverse models of no beginning seriously, we are left with a vision of reality that is almost unrecognizable compared to the traditional picture of a single universe with a singular origin. In these models, what we call the universe is not the totality of existence, but a small subset of a much larger structure. Our observable cosmos, bounded by the limits of light travel time and cosmic expansion, is one region within a boundless framework, a framework that may have been in operation forever. One of the most important shifts in perspective here is that beginnings and endings become local, not global. In eternal inflation, for example, each bubble universe has its own finite history, starting with its own Big Bang and potentially ending in a heat death, a big rip, or a big crunch. But the inflating background that spawns these bubbles has no start or finish. It exists outside the temporal boundaries of any one universe. The same is true for cyclic bounce scenarios. Each expansion and contraction phase is finite, but the chain of cycles extends infinitely in both directions. In such a framework, our universe's story is less about how it began and more about how it fits into the eternal process. The moment we think of as the Big Bang is reframed as a transition point, either from a contracting phase, from a quantum timeless state, or from an inflating background into a non-inflating bubble. The traditional question, what happened before the Big Bang, is replaced by, what is the larger system that produces events like the Big Bang? This shift has a curious effect on how we interpret the arrow of time. In many no-beginning scenarios, the arrow of time is not a fundamental property of the larger reality, but an emergent feature within each local universe. Time's arrow arises from the low entropy conditions at the start of each phase or bubble. In an eternal multiverse, there may be regions where the arrow of time runs in the opposite direction from ours, simply because the entropy gradient there is reversed. This idea is deeply counterintuitive, but in principle it is allowed by the underlying laws of physics. Philosophically, these models confront us with the idea that origin is a relative concept. In a no-beginning reality, every event can be traced back to earlier events, but there is no ultimate first event. This can be unsettling because it denies closure. There is no single answer to, how did it all start? Instead, there is a pattern that repeats or evolves endlessly. For some, this is an unsatisfying retreat from a definitive explanation. For others, it is a liberation from the need for one. A further implication is that the physical laws we observe may themselves be contingent and local. In eternal inflation, different bubble universes can have different laws due to variations in how inflation ends in each region. In cyclic or bounce models, the laws might shift slightly or dramatically between cycles. This opens the possibility that the deep rules of the cosmos are not fixed, but mutable over infinite time. It also suggests that some of our most fundamental constants might be historical accidents, relevant only to our current phase. Testing these bold ideas remains a daunting challenge. The imprints of other universes, pre-bounce phases, or timeless quantum states would be extremely subtle and might be masked by the complexity of later cosmic evolution. Yet, the pursuit of these signatures continues. Improved maps of the cosmic microwave background, more sensitive gravitational wave detectors, and deeper galaxy surveys are all potential tools in the search. Even if we cannot directly observe the larger reality, patterns within our universe might hint at its existence. The search itself is valuable, even if it never yields a definitive detection. By exploring models of a cosmos without a beginning, physicists are forced to push the boundaries of general relativity, quantum mechanics, and thermodynamics. This often leads to new insights and mathematical tools that can be applied to other problems, from black hole physics to the nature of dark energy. In this way, the investigation of no-beginning scenarios enriches physics as a whole. There is also a human dimension to this exploration. For millennia, cultures have created origin stories to explain how the world came to be. The scientific narrative of the Big Bang is, in some sense, our modern origin story. Replacing that with an eternal, self-renewing cosmos would be a profound shift, not just in science, but in our collective imagination. It would change the way we think about our place in the universe, about beginnings and endings, and perhaps even about the meaning of existence itself. In the end, quantum and multiverse models of no beginning are as much philosophical frameworks as they are physical theories. They offer a way to think about reality, in which existence is simply an ongoing fact without a starting point or a creator. Whether or not they turn out to be correct, they expand our conceptual toolkit and remind us that the cosmos may be stranger and more expansive than our current understanding allows. And perhaps that is the most valuable lesson, that in seeking to understand the universe, we must be prepared to imagine realities that stretch far beyond the boundaries of what we can see, measure, or even fully comprehend. In such a vision, our universe is not the first verse in the cosmic poem, nor will it be the last. It is one of countless verses, each with its own rhythm and a form, all woven into a composition without beginning or end, an eternal song echoing through a reality that has always been and will always be. Philosophical and theological implications. When scientists explore the idea of a universe with no beginning, the discussion inevitably spills beyond the boundaries of physics into the domains of philosophy and theology. This is because the question of whether the universe had a starting point is not purely a scientific matter. It touches on some of the oldest and most profound human inquiries. Why is there something rather than nothing? Does the cosmos have a purpose? Is there a deeper reality beyond what science can measure? In a no-beginning framework, these questions take on new forms, sometimes becoming sharper, sometimes dissolving into different lines of thought altogether. From a philosophical standpoint, the notion of an eternal universe challenges the human tendency to think in terms of origins. In everyday experience, everything we encounter comes into existence at some point. Trees grow from seeds, rivers begin at springs, and buildings are constructed from raw materials. We are so accustomed to this pattern that it seems natural to apply it to the universe itself. The Big Bang model fits neatly into this mindset. It is the seed from which everything else has grown. But if the universe has no beginning, this entire mental framework must be revised. The cosmos would not be a product of a prior event. Instead, existence itself would be the default state. This leads to the philosophical concept of a brute fact. A brute fact is something that exists or is true without any deeper explanation. In a no-beginning universe, the existence of the cosmos could be seen as a brute fact. It simply is, and there is no reason why it is rather than is not. For some philosophers, this is a perfectly acceptable stopping point. After all, every explanatory chain must end somewhere. If you keep asking why, you will eventually reach an answer that cannot be explained in terms of something else. For others, however, the idea of a brute fact feels incomplete or unsatisfying because it appears to leave the deepest question unanswered. Theological implications are even more complex. Many religious traditions posit a creator who brought the universe into existence. In such frameworks, the existence of a beginning is often central to the concept of divine creation. If the universe has always existed, this could appear to challenge the idea of a creation event. However, theologians have long debated whether an eternal universe is incompatible with theism. Some argue that a divine being could sustain an eternal universe just as easily as create one from nothing, and that creation need not refer to a single moment in time, but could instead describe an ongoing relationship between the divine and the cosmos. Historically, this debate played out in medieval philosophy. Islamic philosophers such as Avicenna and Averroes, as well as Christian thinkers like Thomas Aquinas, grappled with Aristotle's view of an eternal universe. Aristotle held that the cosmos had no beginning, a view that was at odds with certain theological doctrines of creation. Aquinas, while personally accepting the doctrine of creation in time, argued that reason alone could not prove whether the universe had a beginning or had existed forever. Both possibilities were logically consistent, and the choice between them ultimately rested on revelation, not philosophy. In modern times, the Big Bang model was initially embraced by some religious thinkers as aligning well with the concept of a creation moment. Georges Lemaitre, a Belgian priest and physicist who was one of the pioneers of Big Bang theory, saw no conflict between his scientific work and his religious beliefs, but he was also careful to keep them separate. Conversely, the steady-state theory appealed to those who preferred an eternal universe, whether for philosophical, aesthetic, or theological reasons. The contemporary resurgence of no-beginning models reopens these old debates in a new scientific context. One theological adaptation to an eternal cosmos is the concept of continuous creation. In this view, creation is not a one-time event, but an ongoing process, with the divine continuously sustaining and renewing the universe. This perspective can be found in certain strands of process theology, as well as in mystical traditions that see creation as a constant unfolding rather than a completed act. Such a framework is compatible with both a finite and an infinite universe, because it focuses on the relationship between the divine and the cosmos, rather than on a specific starting point. Another philosophical angle is the impact of an eternal universe on existential meaning. Some people find comfort in the idea of a cosmos with no beginning or end, seeing it as a grand, self-sustaining system in which we are a small but real part. Others find it alienating, as it can make human life feel insignificant in the face of endless time. If the universe has existed forever, then our brief existence occupies an infinitesimal fraction of cosmic history, raising questions about whether our lives have any lasting importance in the grand scheme. On the other hand, one could argue that meaning does not depend on cosmic scale or permanence. Just as a fleeting sunset can be deeply meaningful to an observer, a finite human life can hold significance regardless of its place in an eternal universe. From this perspective, the absence of a cosmic beginning does not diminish meaning, but shifts its source from the universe's structure to the quality of our experiences and actions. The problem of infinity also looms large in these discussions. Philosophers have long debated whether an actual infinite, such as an infinite past, is possible in reality or only as a mathematical abstraction. The famous Hilbert's Hotel paradox illustrates some of the counterintuitive properties of infinite sets. A hotel with infinitely many rooms can still accommodate more guests even when it's full, simply by shifting each guest to the next room. While this is logically consistent in mathematics, some argue that such infinities cannot exist in the physical world. If they are correct, a universe with an infinite past might be impossible, forcing us to reconsider even the most elegant no-beginning models. From an epistemological perspective, a no-beginning universe challenges our methods of inquiry. If the cosmos has existed forever, then there is no earliest moment to study, and any attempt to reconstruct its history will always run into a horizon beyond which we cannot see. This raises the possibility that some questions about the universe's past are fundamentally unanswerable, not because of technological limitations, but because of the nature of reality itself. Such a limit forces us to grapple with the boundaries of human knowledge and to accept that our understanding may always be partial. In this way, the philosophical and theological implications of a no-beginning universe extend far beyond the specifics of any single model. They touch on questions about the nature of existence, the limits of explanation, the possibility of the infinite, and the sources of meaning in human life. They remind us that cosmology is not just a branch of physics, but a field that intersects with some of the deepest currents in human thought. The discussion of a universe without a beginning often circles back to one of the oldest philosophical questions: can something exist without a cause? In our everyday reasoning, causes and effects form an unbroken chain. Every event we observe is the result of some prior event. But if the universe has no beginning, then this chain has no first link. This challenges the principle of sufficient reason, the idea that everything must have an explanation. Some philosophers respond by modifying the principle. Perhaps the requirement for an explanation applies only within the universe, not to the universe as a whole. In this view, the cosmos simply exists as a brute fact, needing no cause beyond itself. This has parallels in certain strands of ancient philosophy. In Aristotle's model, the universe was eternal and uncaused, with motion and change sustained by the unmoved mover, a timeless entity that serves as the ultimate explanation for all motion without itself having a beginning. For Aristotle, the unmoved mover was not a creator in the temporal sense, but an eternal cause in the sense of being the ultimate reason why the universe is ordered as it is. While modern no-beginning cosmologies do not typically invoke metaphysical agents, the idea that the cosmos may be eternal and self-sustaining echoes Aristotle's framework. From a theological standpoint, the possibility of an eternal universe does not necessarily eliminate the role of a creator. Many theologians, including Thomas Aquinas, argued that creation is not synonymous with having a beginning in time. Instead, creation can be understood as the dependence of the universe on a sustaining cause for its existence, regardless of whether it has existed for a finite or infinite duration. In this way, an eternal universe could still be created in the sense of being contingent upon a deeper reality or a divine will. This distinction between temporal creation and ontological creation is crucial. Temporal creation refers to bringing something into existence at a specific moment in time. Ontological creation refers to the ongoing act of sustaining a thing's existence. Even if time has no beginning, the universe could still depend on something beyond itself to exist at all. This line of reasoning allows for theological compatibility with certain eternal cosmologies, reframing creation as a continuous relationship rather than a single event. Philosophically, the concept of an infinite past raises challenging questions about the nature of time. Is time something that exists independently, flowing forever into the past and future? Or is it a property that emerges from the arrangement and change of events? In a universe with no beginning, time would have to be either an infinite backdrop or an emergent phenomenon without a first moment. The emergent time view has become more prominent in certain areas of physics, especially in quantum gravity, where time may not exist as a fundamental entity at all. If this is the case, the question, how long has the universe existed, may turn out to be meaningless in the most fundamental description of reality. The issue of actual infinities plays a major role in this debate. While mathematics can handle infinities with ease, physical reality may not. Some philosophers and physicists argue that an infinite sequence of past events is impossible because it would require completing an infinite number of moments to reach the present, a task they consider logically incoherent. Others counter that if time is eternal, there is no completion of an infinite sequence. The present moment simply exists within that sequence, with no need for a starting point. This debate remains unresolved, and it touches on the deep relationship between mathematical concepts and physical reality. Another implication of an eternal universe concerns cosmological fine-tuning. In a finite-age universe, the apparent fine-tuning of physical constants for life might suggest that special conditions were set at the beginning. But in an infinite cosmos, whether infinite in space, time, or both, fine-tuning could be explained statistically. Given infinite trials, even extremely improbable configurations will occur somewhere or somewhen, and observers will naturally find themselves in regions where conditions are suitable for their existence. This reasoning aligns with the anthropic principle, though critics argue that it can be unfalsifiable and may reduce explanatory rigor. An eternal universe also shifts the existential perspective on human history. In a cosmos with a beginning, all of history is contained within a finite span, and humanity's emergence can be seen as a unique event within that timeline. In an eternal cosmos, however, it becomes at least conceivable that life, perhaps even intelligent life, has arisen countless times before, in regions or cycles beyond our observational reach. This raises both thrilling and unsettling possibilities, that we are part of a vast, repeating pattern, and that the uniqueness we attribute to our own era may be an illusion. From the standpoint of meaning and purpose, opinions diverge sharply. Some find an eternal universe inspiring because it implies that existence is an intrinsic feature of reality, not a temporary anomaly. Others feel that without a definitive beginning or end, existence lacks narrative structure and therefore feels less meaningful. This tension reflects broader human tendencies. Some of us seek security in permanence, others in stories with beginnings and endings. Theology also grapples with the implications for eschatology, the study of last things. In traditions with an eternal universe, the concept of a final judgment or ultimate destiny might be reframed not as the end of the cosmos, but as the culmination of a particular phase or cycle. In cyclic models, theological interpretations might focus on renewal and transformation rather than final closure. This can harmonize with certain religious narratives that emphasize ongoing creation and recreation, rather than a single linear history. In the realm of philosophy of science, a no-beginning universe challenges our ideas about explanatory completeness. Scientific explanations often rely on initial conditions plus laws of nature to predict outcomes. In an eternal universe, there is no set of initial conditions, only ongoing conditions. This means that the explanatory framework must shift from "why did the universe start this way?" to "why is the universe structured this way at all times?" That shift changes the type of answers science can hope to provide. Finally, the contemplation of a universe without a beginning invites humility. It forces us to confront the possibility that our deepest intuitions about time, causality, and origin might be products of our limited, human-scale experience. Just as earlier generations had to abandon the geocentric view of the cosmos, we may need to abandon the idea that the universe must have a temporal starting point. This does not diminish our capacity to understand. Rather, it expands it, pushing us to imagine forms of existence beyond the reach of common sense. One of the most profound philosophical shifts that arises from the idea of a no-beginning universe is the redefinition of contingency and necessity. In a finite-age universe, it is natural to think of the cosmos as contingent, dependent on something else for its existence, such as a cause, an initiating event, or a creator. But if the universe has existed eternally, it begins to look more like a necessary entity, existing by the nature of what it is, rather than by the result of some prior condition. This is not to say it is logically necessary. There could still be alternative metaphysical possibilities, but rather that, in this view, its existence is not the kind of thing that demands a temporal origin. This conceptual shift has resonances with certain strands of metaphysical naturalism, which hold that the cosmos, or the totality of reality, is the ultimate context for everything, not something that itself requires a context. In such a worldview, the universe, or multiverse, is the ground of being, and all questions about its origin are misplaced in the same way that asking what is north of the North Pole is misplaced. The emphasis is not on why it began, but on what its intrinsic properties are and how they give rise to everything within it. For many theologians, however, even an eternal universe does not escape the category of contingency. From their perspective, the universe, whether finite or infinite, does not have to exist at all. It is contingent because it could have been otherwise or not existed at all, and therefore it still calls for an explanation beyond itself. In classical theism, this explanation is God, who is conceived as necessary, eternal, and self-existent, in contrast to the universe's contingent status. This line of thought allows for an eternal creation, in which God has always been creating and sustaining the universe without a starting point in time. Another philosophical challenge that an infinite past raises is the so-called infinite regress problem. In many explanatory contexts, an infinite regress is seen as undesirable because it never reaches a foundational explanation. If every event is explained by a prior event, and there is no first event, then the explanatory chain seems incomplete. Critics of the infinite past hypothesis argue that, without a foundational cause, the whole sequence is left unexplained. Defenders counter that the demand for a foundational cause may itself be an unwarranted assumption, and that, in some cases, an infinite regress is a perfectly acceptable explanation if the regress itself is well-defined and stable. The notion of stability is key here. For an eternal universe to be plausible, it must avoid scenarios in which physical or logical instabilities would have destroyed it long ago. This ties into discussions about entropy and the arrow of time. If entropy has been increasing forever, How is it that we still live in a universe with structure and complexity rather than in a state of maximum disorder? One possible answer is that our observable universe is just a small, low-entropy fluctuation within a much larger, high-entropy background. While such fluctuations are extraordinarily improbable on short time scales, in an eternal context, they become inevitable. However, this leads to the Boltzmann brain problem. The idea that in a vastly old universe, it should be far more probable for random fluctuations to produce isolated, self-aware observers than entire structured universes like ours. Since we appear to inhabit the latter, some take this as evidence against certain eternal universe scenarios. From the standpoint of meaning, a no-beginning universe can cut two ways. On one hand, the sheer scale and timelessness of such a reality can inspire awe, giving human existence a place in a grand, ongoing process. On the other hand, it can provoke a sense of insignificance. If there has been infinite time before us and will be infinite time after, then our individual and collective stories may feel like infinitesimal blips with no enduring impact. Philosophers have long debated whether significance requires permanence, with some arguing that meaning is found in the moment and others contending that it depends on lasting consequence. Theological systems that embrace an eternal universe often reframe the purpose of creation. Instead of aiming at a final culmination or resolution, creation may be understood as an endless unfolding of divine creativity. This fits well with cyclical cosmologies, in which the universe goes through endless phases of birth, growth, decline, and renewal. In such systems, meaning is derived not from a linear progression toward a final goal, but from participation in the ongoing rhythm of existence. Interestingly, the idea of an eternal universe also has implications for theodicy, the attempt to reconcile the existence of evil with the existence of a good and powerful creator. In a finite universe, the presence of suffering might be explained in part by the constraints of creation at a particular moment, or in a particular history. In an eternal universe, however, suffering and imperfection may be seen as eternal companions to existence itself, raising deep questions about whether they can ever be eliminated. This has led some theologians to explore models in which the divine purpose is not the eradication of imperfection, but its perpetual transformation. From a philosophical logic perspective, the infinite past hypothesis invites comparisons with other types of infinities in mathematics and metaphysics. In mathematics, infinite sets can be consistent and well-defined. In physics, infinity often signals a breakdown of the model. If the universe truly has an infinite past, then it would represent a physical realization of an abstract mathematical infinity. Whether such a thing is possible, or whether it points to the need for a more fundamental, possibly finite description, is still an open question. Finally, there is the epistemic humility that comes with contemplating a universe without a beginning. The absence of a temporal starting point means that our observational reach will always be limited to a finite segment of an infinite reality. No matter how advanced our instruments become, there will always be an unobservable infinity behind us in time. This is a sobering reminder that human knowledge, no matter how powerful, will always operate within horizons, both physical and conceptual, that we cannot cross. If the universe has no beginning, the implications ripple through every level of human thought, from our scientific models to our philosophical assumptions to our spiritual narratives. One of the clearest shifts is the way such a framework redefines the role of cosmology itself. In a finite-age universe, cosmology aims to trace the story of the cosmos back to its origin, identifying the conditions and events that mark the beginning. In a no-beginning universe, the goal changes. Instead of searching for a first moment, the emphasis falls on understanding the ongoing structures and processes that sustain reality through infinite time. This change in focus requires a subtle but important adjustment in how we think about explanation. In a finite framework, ultimate explanations are often historical. We explain the present by appealing to an earlier state. In an eternal framework, ultimate explanations must be structural. We explain the present by identifying principles that hold across all of time, without appealing to an initial condition. This kind of explanation is more like describing the rules of a game than recounting how the first move was made. Philosophically, this demands that we examine whether our concept of causality can even be applied to the universe as a whole. In everyday life, causality is tied to temporal sequence. Cause comes before effect. But if the universe has existed forever, there is no earliest cause, and causality may instead be a network of relationships that exists all at once, rather than a chain that began somewhere. Some thinkers propose that reality is fundamentally atemporal, and that time as we experience it is a derived feature of a deeper, timeless order. In such a view, the question, why is there something rather than nothing, might be transformed into, why is the structure of reality this way, rather than another way? Theologically, an eternal universe can shift the understanding of divine action. In traditions that hold to a creator, an infinite cosmos may be seen as a more fitting expression of divine infinity than a finite one. If God is eternal and unlimited, then an eternal act of creation could be a more coherent reflection of that nature than a one-time act. In this interpretation, the universe's eternity is not a challenge to divine creation, but a manifestation of it. This idea appears in some strands of Islamic philosophy, certain interpretations of Hindu cosmology, and mystical branches of Christianity. However, a no-beginning model can also intensify some theological tensions. For example, if the universe is eternal, then it may also be eternally subject to suffering, decay, and imperfection. The idea of a final redemption or an ultimate end to suffering, central to many religious traditions, may need to be reinterpreted as something cyclical, partial, or symbolic, rather than a literal conclusion to history. This could be unsettling to believers whose hope is tied to a definitive, transformative endpoint. The question of meaning also undergoes transformation in an eternal universe. In a finite cosmos with a clear beginning and end, it is easy to frame meaning in terms of a journey from origin to destiny. In an eternal cosmos, meaning may need to be found in participation, in the quality of engagement with the ongoing process of existence, rather than in reaching a final goal. This perspective aligns with philosophical traditions that emphasize the intrinsic value of life's moments, rather than their contribution to an overarching endpoint. Another area impacted by the no-beginning concept is moral philosophy. If time stretches infinitely in both directions, then every moral action is embedded in an endless continuum of events. Some might argue that this dilutes the significance of any single choice, while others contend that it heightens significance. Since in an eternal reality, even the smallest acts are part of an unending tapestry, the challenge lies in articulating ethical systems that retain meaning in the absence of cosmic finality. From an epistemological standpoint, accepting a no-beginning universe is an act of humility. It means acknowledging that the ultimate structure of reality may be permanently beyond our observational grasp. Even if our theories point toward eternity, we will always be inferring that eternity from a finite dataset. This limitation does not make the idea less valuable. Indeed, it mirrors the way we accept other scientific conclusions that extend far beyond direct observation, such as the existence of atoms or the curvature of space-time. The possibility of an eternal universe also reframes the human narrative in the cosmos. We are not at the midpoint of a finite story, nor are we at the start of a new chapter in a cosmic drama with a definite conclusion. Instead, we are in a moment, unique, transient, and yet inseparably part of an infinite continuum. This view can inspire both humility and empowerment. Humility in recognizing our smallness in the face of infinity, and empowerment in realizing that our moment, however brief, is a necessary and irreplaceable part of the whole. In closing, the philosophical and theological implications of a no-beginning universe are as vast as the concept itself. They invite us to reconsider our assumptions about causality, creation, meaning, and purpose. They challenge us to imagine a reality where time has no starting line, where existence is not a question of origin, but of ongoing being. Whether such a universe actually exists is still unknown, and may remain unknown. But the exercise of thinking about it stretches the human mind beyond familiar boundaries, reminding us that the cosmos is not obliged to conform to our intuitions, and that our search for understanding is itself an eternal endeavor. Observational challenges and the search for evidence. When we talk about a universe with no beginning, the theories are often elegant, mathematically rich, and conceptually fascinating. But they face a major hurdle: evidence. Physics is, at its core, an empirical science. However compelling a model may be, it must eventually meet the test of observation and experiment. For cosmological models without a beginning, this test is particularly difficult because they often make claims about conditions or events that lie far beyond our direct observational reach. The challenge is not simply to find evidence that could confirm these models, but to determine whether such evidence is even possible to obtain. One fundamental problem is the observational horizon. The observable universe is limited by the speed of light and the finite time since the hot Big Bang phase began. Light has only had about 13.8 billion years to reach us, which means we can see only as far as light could travel in that time. Due to cosmic expansion, the radius of the observable universe is actually about 46 billion light-years, but beyond that, we cannot see. Those regions are causally disconnected from us. If anything relevant to the before of our universe happened outside this horizon, it is invisible to us in principle. A second problem is the opacity of the early universe. Even within the observable universe, we cannot see arbitrarily far back in time using light. For roughly the first 380,000 years after the Big Bang, the universe was a hot, opaque plasma of electrons and protons. Photons could not travel freely without scattering off charged particles. Only when the universe cooled enough for atoms to form, a process called recombination, did light begin to travel through space unimpeded, producing the cosmic microwave background, CMB, we detect today. This means that, using light, our window into the past stops at that surface of last scattering. Anything before that is invisible to traditional telescopes. Because of these limits, cosmologists must rely on indirect methods to probe earlier times or pre-Big Bang phases. One promising approach is to look for imprints that such earlier conditions might have left on the CMB. For example, certain bounce models predict subtle deviations from the nearly perfect Gaussian distribution of temperature fluctuations in the CMB. These deviations might take the form of specific patterns of non-Gaussianity, anisotropies at large angular scales, or unusual alignments. Detecting such patterns would not prove a no-beginning model, but it could provide hints that something happened before the standard inflationary period. Another avenue is primordial gravitational waves. Unlike light, gravitational waves interact very weakly with matter, allowing them to travel virtually unimpeded from the earliest moments of the universe. In principle, they could carry information from times even before the CMB was released. The challenge is that these primordial waves are extremely faint. Current gravitational wave detectors like LIGO and Virgo are designed to detect waves from astrophysical sources such as black hole mergers, not the ultra-low frequency waves from the early universe. To detect primordial gravitational waves, we would need space-based detectors such as the proposed LISA mission, or even more ambitious concepts like pulsar timing, arrays extended over decades. The difficulty is compounded by the fact that different no-beginning models can produce very similar observational signatures. For example, both certain inflationary models and some bounce scenarios predict a nearly scale-invariant spectrum of density fluctuations. This means that even if we detect a feature consistent with a bounce, it might also be explained by inflation. Distinguishing between these possibilities requires extremely precise measurements and a clear understanding of all possible sources of similar signals. There is also the problem of cosmic variance, the fact that we have only one universe to observe. In statistics, having multiple independent samples helps reduce uncertainty. In cosmology, we have only one observable universe, which means some uncertainties can never be reduced no matter how good our instruments are. This is particularly relevant for large-scale anomalies in the CMB. Are they hints of pre-Big Bang physics, or just statistical flukes in our one data set? Without another universe to compare to, we may never know for sure. Even if we could gather the right kind of data, interpreting it is a challenge. Cosmological models are built from a combination of fundamental physics and assumptions about initial or boundary conditions. The same observational signature can sometimes be reproduced by multiple different models. For instance, a certain pattern in the CMB could be explained by a pre-Big Bang feature, by unusual physics during inflation, or by foreground effects like galactic dust. Disentangling these possibilities requires not only better data, but also better theoretical understanding. Some researchers have turned to large-scale structure surveys as another source of evidence. The distribution of galaxies, galaxy clusters, and cosmic voids reflects the primordial fluctuations from which they grew. If those fluctuations were influenced by processes before the standard Big Bang phase, they might leave detectable signatures in the large-scale structure. Upcoming surveys, such as those by the Euclid Space Telescope and the Vera C. Rubin Observatory, aim to map the distribution of matter across a huge fraction of the observable universe, potentially revealing patterns that hint at pre-Big Bang physics. Another possible observational handle is the study of high-energy cosmic particles. Ultra-high-energy cosmic rays and neutrinos could, in principle, carry information from processes very early in the universe's history. While these particles are subject to scattering and energy loss, their detection could still offer indirect clues. However, linking any such observations to a no-beginning model would be extremely difficult, as many astrophysical sources could produce similar signals. The most sobering possibility is that the evidence we seek may be fundamentally inaccessible. If the pre-Big Bang phase erased its own traces, either through inflation, through a bounce that fully reset conditions, or through quantum effects that render earlier states indeterminate, then no amount of observation will ever reveal it. In that case, the question of whether the universe had a beginning might remain forever in the realm of theory, not empirical science. This is a frustrating prospect, but it is one that cosmologists must take seriously. Yet even with these challenges, the search continues. The reason is not just curiosity about origins. It is that probing these limits pushes the boundaries of our technology and our understanding of physics. In attempting to test no-beginning models, we are also refining our knowledge of the universe's earliest moments, the behavior of matter and energy at extreme conditions, and the interplay between quantum mechanics and gravity. Even if we never find definitive proof, the journey enriches our grasp of the cosmos. One of the first targets for testing no-beginning models is the cosmic microwave background, CMB, because it is the oldest direct light we can observe. The CMB acts like a vast fossil record, encoding conditions in the universe when it was only 380,000 years old. In standard cosmology, its patterns are explained by inflation, a brief period of exponential expansion shortly after the Big Bang. However, certain no-beginning models, such as bouncing cosmologies, predict subtle differences in the CMB's statistical properties that inflation does not naturally produce. Detecting these differences would require precision far beyond current measurements. But the CMB remains a prime observational battleground for these ideas. For example, some bouncing models predict a suppression of power at the largest angular scales in the CMB, potentially matching hints of such suppression already observed by the Planck satellite. However, the statistical significance of these anomalies is low, and they could simply be chance fluctuations. Other predictions include small oscillatory features in the CMB power spectrum, arising from pre-bounce physics. Detecting such features would not only require high sensitivity, but also careful separation from noise and foreground contamination, such as emission from our own galaxy. A complementary approach is to search for non-Gaussianity, departures from the simple random distribution of temperature fluctuations. Inflation generally predicts that these fluctuations should be nearly Gaussian, whereas certain cyclic or emergent models may produce distinctive non-Gaussian signatures. These might take the form of specific shapes in the three-point correlation function, known as the bispectrum, or even higher-order correlations. So far, observations have found only tiny deviations from Gaussianity, but future missions like CMB-S4 aim to improve sensitivity by an order of magnitude. Beyond the CMB, large-scale structure LSS surveys provide another avenue for testing no-beginning models. The formation of galaxies and clusters traces the growth of initial density fluctuations over cosmic time. If those fluctuations were seeded by processes before the hot Big Bang phase, their statistical properties might differ subtly from those expected in a purely inflationary scenario. Features such as oscillations in the matter, power spectrum, correlations at specific scales, or unusual alignments could hint at pre-Big Bang physics. Projects like the Dark Energy Spectroscopic Instrument, DSI, and Euclid are mapping millions of galaxies to unprecedented precision, potentially offering new clues. However, interpreting LSS data is complicated by nonlinear evolution. The fact that gravitational collapse distorts the original patterns in ways that can obscure their origins. This is where high-performance simulations become essential. By running cosmological simulations under different no-beginning scenarios, researchers can predict how initial conditions from a bounce or an emergent phase might propagate into today's structure. Comparing these predictions to real data could help narrow the field, even if definitive proof remains elusive. Gravitational waves also remain a promising but challenging source of information. In principle, gravitational waves from a pre-Big Bang era could survive into the present day. Their imprint might be seen indirectly in the polarization patterns of the CMB, specifically in the so-called B modes. Inflation predicts a certain spectrum of primordial gravitational waves. Bouncing models can produce different spectra, potentially even enhancing power at very large scales. The difficulty is that the B-mode signal from gravitational waves is extremely faint, and foreground sources like dust in our galaxy can mimic it. The BICEP and Keck array experiments famously announced a detection in 2014 that was later shown to be entirely due to dust, illustrating just how tricky this measurement is. Another experimental frontier is the detection of very low-frequency gravitational waves through pulsar timing arrays, PTAs. PTAs monitor the arrival times of pulses from millisecond pulsars with extraordinary precision. Passing gravitational waves slightly stretch and compress the space between Earth and the pulsars, causing correlated shifts in the pulse arrival times. While current PTA results are probing signals from supermassive black hole binaries, future improvements might make it possible to detect a stochastic background from the early universe. Whether this background could reveal evidence of a pre-Big Bang phase depends on its amplitude and spectral shape, parameters that are highly model-dependent. High-energy astrophysics also enters the picture. Some no-beginning scenarios predict that remnants of earlier cosmic cycles could survive into our current phase, perhaps as unusual black holes, exotic particles, or specific distributions of dark matter. For example, primordial black holes formed before the hot Big Bang phase could act as seeds for galaxy formation or make up a fraction of dark matter. Detecting such objects and distinguishing them from those formed later would be a major observational breakthrough. At the particle physics frontier, experiments like those at the Large Hadron Collider, LHC, or future colliders could provide indirect support for no-beginning models by uncovering new physics relevant to the very early universe. For instance, discovering evidence for extra dimensions, new scalar fields, or violations of certain symmetries could bolster the plausibility of specific pre-Big Bang scenarios. While such discoveries would not prove a no-beginning universe, they could point toward the kinds of high-energy conditions in which such models become natural. Yet, for all these possibilities, a sobering reality persists. Most of the evidence for or against a no-beginning universe is likely to remain circumstantial. The reason is that the physics of the very early universe, or any phase before it, often lies at energies and densities far beyond what we can reproduce in a laboratory. Even with the most powerful telescopes and detectors, we are peering through an observational keyhole at a vast and mostly hidden reality. That is why theoretical work remains as important as observational work in this area. By developing models that are mathematically consistent, physically plausible, and compatible with known data, theorists can help guide observations toward the most promising tests. At the same time, observational results can feed back into theory, ruling out certain possibilities and sharpening others. This interplay between theory and observation is the lifeblood of cosmology, especially in domains where direct evidence is scarce. While the search for direct observational evidence for a no-beginning universe is fraught with difficulties, it is not without strategy. Scientists often adopt a multi-pronged approach. Rather than expecting a single smoking gun signature, they look for a convergence of independent observations that all point toward the same conclusion. This method has been used successfully in other areas of cosmology. For example, in establishing the existence of dark energy, where evidence came from supernova surveys CMB measurements, and large-scale structure studies. Applying a similar methodology to the question of cosmic origins increases the robustness of any claims, even if each individual line of evidence remains inconclusive on its own. One possible pathway involves the study of cosmic relics. These are physical remnants from earlier stages of the universe that survive to the present day. The CMB is the most famous example, but there could be other relics, particles, fields, or structures, originating in a pre-Big Bang era. For instance, certain models predict that topological defects, such as cosmic strings or domain walls, might have formed during phase transitions in the early universe. If these structures were generated before our current expansion phase, their properties might carry information about that earlier epoch. Observations of their gravitational lensing effects or gravitational wave emissions could offer clues. However, the non-detection of such relics also constrains no-beginning models. If a given scenario predicts a relic population that should be observable today, and we fail to find it despite having the sensitivity to do so, that model is weakened. This is one of the few ways that observational data can decisively rule out specific eternal universe proposals. The challenge is that many models can be tuned to suppress unwanted relics, making them harder to falsify. Another avenue is the hunt for imprints in the statistical distribution of matter and radiation. This is a subtle business because the standard cosmological model, lambda CDM with inflation, already explains most of the observed large-scale features extremely well. Any deviation from these predictions must be small enough to have escaped detection so far, but large enough to be detectable with improved instruments. This is a narrow window, but not an impossible one. The next generation of CMB experiments, combined with deep galaxy surveys, could potentially reveal such deviations. Yet, even if such deviations are found, interpretation will remain a central challenge. A suppressed power spectrum at large scales, for instance, could be taken as evidence for a pre-Big Bang contracting phase, but it could also arise from features in the inflationary potential, or even from unexpected astrophysical foregrounds. In this sense, cosmology suffers from a degeneracy problem. Multiple theoretical mechanisms can produce the same observational signatures. Breaking these degeneracies requires either finding multiple, independent effects predicted by the same model, or discovering a feature that is uniquely associated with a particular scenario. For this reason, some researchers advocate for a broader approach that includes not just cosmology, but also high-energy physics, astrophysics, and even analog experiments in the laboratory. For example, certain aspects of spacetime behavior near the bounce in cyclic models could be explored through analog systems in condensed matter physics, such as Bose-Einstein condensates or superfluid helium. These systems can simulate some of the mathematical structures of spacetime in a controlled environment, offering a way to test the internal consistency of models even if they cannot directly probe the actual early universe. In parallel, the search for exotic astrophysical objects may provide indirect hints. Primordial black holes, PBHs, are a prime example. While inflation can also produce PBHs, certain no-beginning models predict distinctive mass distributions or spatial clustering patterns for these objects. Detecting such features would not be definitive proof, but it could provide a strong motivation to take the model seriously. Similarly, the detection of extremely massive black holes at unexpectedly early cosmic times could challenge the standard model and suggest the influence of pre-Big Bang conditions. The role of computational cosmology in this quest cannot be overstated. Modern simulations can evolve billions of particles under the influence of gravity and other forces, tracking the growth of cosmic structure from the earliest times to the present. By feeding these simulations with initial conditions from different no-beginning scenarios, researchers can generate mock universes to see how they compare with our own. These simulations can predict, for example, the expected frequency of certain galaxy types, the size distribution of cosmic voids, or the statistical properties of the intergalactic medium. Observational campaigns can then test these predictions. Yet, despite all these tools, we may have to accept that the question, "Did the universe have a beginning?" will never be settled definitively by observation alone. This is not because the question is meaningless, but because it may lie in the category of scientific questions, whose answers depend on both empirical evidence and theoretical coherence. In other words, the best model might be the one that fits all available data, is internally consistent, and meshes well with our broader understanding of physics, even if some of its predictions remain forever beyond direct observational reach. That is why philosophers of science have a role to play here. They can help clarify the criteria by which we judge one cosmological model to be better than another, especially in cases where empirical tests are limited. Should we favor simplicity, mathematical elegance, explanatory breadth, or predictive power? Each of these virtues can point in a different direction. And in a field as speculative as early universe cosmology, the balance between them is delicate. In the end, the search for evidence of a no-beginning universe may not culminate in a single decisive discovery. Instead, it may be a gradual accumulation of clues, a statistical pattern here, a relic particle there, a theoretical breakthrough that makes one scenario vastly more plausible than its rivals. The journey may be long and uncertain, but the pursuit itself will continue to push the frontiers of observation, theory, and human imagination. The final dimension of the observational challenge lies in the recognition that our tools, however advanced, are products of the universe we inhabit. This means they are inherently limited by the laws of physics as we understand them, and the particular conditions of our observable cosmos. If there was a pre-Big Bang phase with radically different physical laws or space-time structure, then not only might its signals be inaccessible, they might be fundamentally incomprehensible to us. This is a sobering possibility, that there could be aspects of reality that no amount of technological or intellectual progress would allow us to uncover. Yet history shows that limits often turn out to be temporary. There was a time when the idea of seeing beyond our galaxy was inconceivable. The Milky Way was thought to be the entire universe. Likewise, there was a time when the cosmic microwave background was entirely unknown. Both of these boundaries were shattered by advances in observation and theory. It is therefore reasonable to hold that some of the current barriers to probing a no-beginning universe may one day be overcome. Technological innovation, whether in detectors, data analysis, or entirely new observational methods, has a track record of expanding our horizons. For example, speculative proposals such as using quantum entanglement for astronomical measurements or exploiting neutrino astronomy on cosmic scales could open windows onto epochs that are now opaque to electromagnetic observations. Neutrinos, like gravitational waves, interact only weakly with matter, and thus could carry information from the earliest instance, or from a pre-Big Bang phase, almost unaltered. The technical challenge of building detectors sensitive enough to capture such faint, cosmic neutrino backgrounds is enormous, but not impossible in principle. Another frontier is the synergy between different observational channels. Multi-messenger astronomy, which combines electromagnetic, gravitational wave, neutrino, and cosmic ray data, has already revolutionized our understanding of astrophysical events like neutron star mergers. Extending this approach to cosmology could yield new insights. If, for instance, a background of gravitational waves from a cosmic bounce were detected in concert with a peculiar neutrino signature, the combined evidence might be far more persuasive than either signal alone. It is also worth considering that the best evidence for a no-beginning universe may come not from looking farther back, but from looking more deeply into the present. The structure and behavior of dark matter, dark energy, and quantum fields in today's cosmos could contain subtle fingerprints of an eternal past. For example, certain cyclic models predict specific relationships between the properties of dark energy and the geometry of space. Measuring these with high precision could help discriminate between a universe with a finite age and one with an infinite history. In addition, laboratory experiments probing the foundations of quantum mechanics and gravity could indirectly inform our understanding of the universe's origins. If new physics emerges, such as evidence for a quantum theory of gravity, it could radically alter the plausibility of certain no-beginning models. For instance, loop quantum gravity naturally leads to bounce cosmologies, while some versions of string theory allow for eternally existing higher dimensional spaces from which our universe could have emerged. Still, even in the most optimistic scenario, the observational case for a no-beginning universe will almost certainly remain probabilistic. Scientists will weigh competing models against a mix of evidence, plausibility, and explanatory power. The aim will not be to reach absolute certainty, but to gradually increase confidence in the models that best account for what we observe while remaining consistent with fundamental physics. Perhaps this is fitting. The question of whether the universe had a beginning is, in many ways, the ultimate question of origins. It touches on physics, philosophy, and metaphysics all at once. The search for an answer drives us to push the boundaries of observation and theory, to confront the limits of knowledge, and to imagine realities far beyond the familiar. Even if the answer remains forever just out of reach, the pursuit shapes the way we see the cosmos and our place within it. In closing, the observational challenges to testing a no-beginning universe are immense, but not insurmountable in spirit. We may never have a definitive view of what lies beyond the observable horizon. Yet, by refining our instruments, expanding our methods, and embracing a broad, interdisciplinary approach, we can continue to chip away at the unknown. Each new observation, however small, adds a piece to the puzzle. And in the process, we not only learn about the cosmos, we learn about the very nature of human curiosity, its persistence, its adaptability, and its refusal to accept the boundaries of the possible without first pressing against them. I hope you enjoyed this journey. If you're still awake, you'll find another fascinating cosmic story right here on the screen. Until next time, and have a good night.